Good morning, everyone. Welcome to the third day of POPL'. It is my great pleasure to introduce our keynote speaker for this morning. Jens Paulsberg is a professor and former department chair of computer science at the University of California, Los Angeles. His research interests span the areas of programming languages, software engineering, and quantum computing. He is the director of the UCLA Amazon Science Hub for Humanity and Artificial Intelligence, an associate editor of ACM Transactions on Quantum Computing, and a member of the ACM Council. He is also a co-director of the Quantum Research Center at UCLA, which has more than 30 professors, and is on the team that started the master's degree in quantum science at UCLA. In 2012, he received the ACM SIGPlan Distinguished Service Award, and in 2023, he received a teaching award at UCLA for his course on quantum computing. And today he's here to tell us about Quantum 3.0, so let's give a warm welcome to Jens.
So welcome to Quantum 3.0. Last year saw a breakthrough in quantum error correction, and that started a new era of quantum computing research. And today I want to talk about the research challenges, and I want to persuade you that now is a great time to join. And I'm going to use 3 points to try to persuade you to join. The first point is that this breakthrough in quantum error correction makes computer science more important to quantum computing research. The second point is that this breakthrough creates an agenda of research, an agenda of essential computer science research that can help move the timeline for when quantum computing will succeed. And the third point is that the breakthrough will bolster the computer science quantum community, specifically the computer science quantum community. And so let me begin with my first point. 2024 was a great year for quantum computing research. And I want to make this point that the breakthrough in quantum error correction makes computer science more important to quantum. Actually, let's begin just with 2 points about quantum computing. A quantum computer is an accelerator, just like a GPU is an accelerator. It will get its work from a CPU, it'll do some work, and it'll pass results back to the CPU. It's a specialized accelerator. It's all about vectors and matrices, but it has something going for it, which is that a quantum computer can run quantum algorithms, some quantum algorithms that are exponentially faster than the classical ones. And so that's a very good way of being specialized. Whenever the quantum computer is good for something, that's when we will use it. And an exponential speed up is very much worth having. And the famous examples are, of course, number one, Shor's algorithm, exponentially faster factoring of integers on a quantum computer, which threatens to break public key crypto. And number two is simulation of physics at the level of atoms and molecules, which was the original vision of Feynman when he started to talk about quantum computing. And again, we will be able to simulate physics exponentially faster than what we can do on a classical computer. And that's the first point. It's something that if we can make that succeed, it will really be worth having. The second point is there's a difference between quantum computing and classical computing, well, in more than one sense, but certainly in this sense, which is that in quantum computing, error correction is a software problem. In this room, most of us are used to that. We can work on the software stack of our classical computers all day, and we never think about error correction, because error correction is in the hardware of classical computing. In quantum computing, it's different. In quantum computing, error correction has to be in the software stack. And the way it works is actually the way all error correction works. It's a question of adding redundancy so that when something goes wrong, we can look at the redundant information and work out what's going on and correct the errors. And the way this comes out in quantum computing is that we have the physical qubits. That's what the physics people are producing. They can be produced by many different technologies. Nowadays, we have a whole variety. One can make qubits with ion traps. One can make qubits with neutral atoms, with spin qubits, or there are superconducting qubits, and there are other emerging technologies. So there's a whole variety of hardware platform for making qubits. Those are the physical qubits. And then one has to realize that they are error prone. They are kind of bad in the sense that if we start to do computation with them, the error rate is so high that the result will be meaningless. And so that's where error correction comes in, and it has to be in software. And so what that means is that we will use many physical qubits to protect a few good qubits, qubits that work like in the math book or in the POPL papers. We will call them logical qubits. So the ones that work perfectly. And then the idea is we will use many physical qubits to protect a few logical qubits. And we will do this protection using error correction exactly the way error correction normally works. And then one can add some skepticism here, which is, well, if we are doing this at the software level and the physical qubits are error-prone, doesn't that just mean that we are going to have very error-prone error correction and it will actually never work? And that's where we have to get to some skeptical points here and dive into this a little bit. So number one, does this work today? Does quantum computing, is it important for business and science today? No, that's years away. Number two, people, a skeptic might say, I have heard that this picture of yours from the previous slide actually is so bad that we need 1,000 physical qubits to support a single logical qubit. That sounds excessive. And indeed, that is a lot. And that is an estimate. That's the best estimate we have today for what we need. And that's a big factor to overcome. And it's definitely a big factor to overcome with adding so many error-prone physical qubits to support a single perfect logical qubit. So there's a problem there. And then there's a third question, which is that the skeptic might say, so how many logical, so let's say you can make logical qubits, but how many of them do you need? And even that question today is unclear. Some people might say 60. Other people will go as high as 1,000. And just to give you a sense, for Shor's algorithm, the best paper we have today is from 2021 by Craig Gidney and Martin Ekero that says that to run Shor's algorithm on an RSA integer of interest to breaking public key crypto, we will need 20 million physical qubits. So you can see even here, if we take the numbers on this slide and say 1,000 logical qubits, each supported by 1,000 physical qubits, that gets us to 1 million. There's still a jump up to 20 million from that paper. So we are talking about big numbers. And so the question is, can we ever make this work? And that's where 2024 comes in. And the question that we should ask ourselves really is the success of quantum computing, is that a physics problem? Or is it a computer science problem? And if it's a computer science problem, is it a programming languages problem? And if we just do a little bit of history, late 50s, Richard Feynman started to talk about the idea of having a quantum computer, and that would be a good idea for simulating physics. And then in the early 90s, Peter Shor invented Shor's algorithm for factoring integers. It was still all theory. I call that quantum 1.0. And then came the late 90s, where people from MIT invented the first quantum computer. So now we actually had some physical qubits, and quantum 2.0 started. Not very many physical qubits. Even today, we have hundreds or thousands of physical qubits on the largest quantum computers, and they're certainly error-prone. 5 years ago was the time when Google announced that they had done a computation on their quantum computer that a classical computer would need thousands of years to do. So we are rolling through quantum 2.0, and then we get to 2024, where people started to make experiments with error correction and show that all the theory we have had of error correction for decades start to work. And the way it starts to work is that we can start to suppress these errors that are there in the physical qubits, and we can start to actually, in a successful way, add the redundancy that we need to get to smaller error rates. And so I would say that what we have today is a few logical-ish qubits. There's still some error rate there, but so far we're just suppressing a little bit. And I'm going to show you how much, so you can make your own judgment here. I put 5 of my favorite papers from 2024 on this slide. I've been very sloppy with the authors. Many of these papers have many, many authors. And what I did to make it fit on a slide was simply to abbreviate a little bit and put the main company as I saw it among the authors on there. So we have papers from Google, from IBM, from Microsoft, from Continuum, from Coursera. And they have all demonstrated that we can suppress errors and that we can work towards building these logical qubits. And in more detail, I have the following extract from the papers. So all of these papers are experimental. And in the first data column there, I show the number of logical qubits. So you can see a small number, certainly not this end goal of 60 to 1,000 that I talked about, but we are sort of beginning to get there. The error rate is in the green column. And so there are two things to know about it, maybe three. The first thing is the error rate is sort of on the order of 10 to the minus 3. So let's call it 0.1% error rate, operating on the logical qubits. And so that's good. The second thing is that what they show is that they can make that error rate better than the error rate for the physical qubits. And the more aggressive error correction they add, the smaller the error rate. At the moment, because this is experimental, there's really a limit to how far we can go, for the simple reason that our quantum computers today only have hundreds or thousands of qubits. But what this is showing is a path towards the end goal, which, at least the way people talk about it today, is to have an error rate on the logical qubits of 10 to the minus 6. And then in the last column is the column that's like the 1,000 number that I had. How many physical qubits do we need to support each logical qubit? And you can see these numbers are not so high, that none of them are 1,000. And that's because the error correction is not as aggressive as what we would need in the future. But it's enough that we get some suppression of the error rate. And so I would say, as part of the computer science agenda that I'm going to advance today, is that we should be more optimistic than going for 1,000 physical qubits to support each logical qubit. We should go for 100. And this thing of optimizing and streamlining and improving things, that's something we can do. And I think we could get there. And so this leads me to the computer science agenda. And I'm going to try to make the point here that this breakthrough in quantum error correction creates an essential agenda where we, computer science, can help advance the timeline of when quantum computing will succeed. And this is my agenda slide here. So the absolutely key point is that the software stack of quantum computing must include error correction. And on the right, I am outlining such a stack. I made 3 levels to make it fit the slide and make it easy to talk about, and I will go into it a little bit. And then on the left are my agenda items. And so let's begin at the top. So a good software stack should have a good interface to the quantum algorithms people want to write. So we need to have a nice high-level language for writing Shor's algorithm and simulation of physics and all the other good algorithms that are coming out this decade. And that should be a level where we only talk about the logical qubits, and all the error correction should be hidden in the stack. And then the way it has to work is that there has to be a step of the compiler, which I here call decomposition and approximation, but where we're really compiling to an intermediate representation, which here I call the fault-tolerant gate set. And fault-tolerant gate set is another way of saying that what the quantum error correction people can do, both the experimental ones and the theoretical ones, is that they can support error correction for certain kinds of quantum gates. And we need to compile to that level. When you read quantum papers or quantum textbooks, you will see that quantum gates can be many different things. But for the purpose of actually error correcting them, so taking the gates and adding this sort of support layer of adding redundancy and doing all the things that need to be done, there's only a subset of those gates where people actually know how to do it. So we need to compile to that subset. That becomes the intermediate representation. And then the second level of the stack can then do all the things that we need for error correction. We need to encode the logical gates, so the gates that work on the logical qubits. We will need to add code for error detection and for error correction, and it will be a lot. There's no doubt that it'll be a lot, because if we're going to have 1,000, or with my optimism, 100 qubits to support each logical qubit, it's clear that this middle layer will add a whole lot of stuff. And so just to give you a sense, I attended a talk on quantum error correction a couple of years ago, and there's a very famous speaker who opens the talk by saying, "What is a quantum computer for?" And of course, nobody dares to say anything when the famous speaker asks a rhetorical question. So he continued by saying, well, you might think that it is for running quantum algorithms, but that would be wrong. Because if we're going to have 1,000 physical qubit to support each logical qubit. Think about it. If you have a quantum computer with 1 million qubits, 999,000 of those qubits are there just to protect 1,000 logical qubits. So actually, all the work is done, well, almost 99.9% of the work is done by code inserted by this middle layer of the software stack. The third layer of the software stack is kind of the rest, where we then compile this error-corrected stuff to the gate set of an actual quantum computer. And then we will have a full compiler. And so we have a compiler problem here. Clearly, the bottom layer needs to know the hardware really well. We definitely have an optimization problem here if we're going to decrease the resource need for supporting a logical qubit from a factor of 1,000 to a factor of 100. We should think about optimality, like we always do in computer science, to know when to stop. And then very importantly, verification. And so let me just dwell on this a bit. When we have a quantum computer running a quantum algorithm that gives us a quantum advantage that is just faster, or maybe much faster than any classical computer can do, then knowing what's going on, knowing that we can trust the results, really comes down to ahead-of-time verification. We can no longer use a classical computer to simulate by definition because we have quantum advantage. And so we really need to verify that all of this stuff works, particularly that the error correction works, which where a lot of this stuff is. We need to verify the quantum algorithms, and we need to verify a lot of the math that's underlying, a lot of lemmas and things that are underlying all of those things. And so that is my agenda. And what is the problem here? The problem is that a lot of the research that have been going on so far have not exactly addressed the software problem with a software stack with error correction in the middle. And so what I'm setting out to do here in this part of the talk is to criticize some papers. And so just to avoid making too many more enemies today, I'm going to criticize my own papers. I'm going to start with something straightforward, which is conditionals. So quantum computing needs conditionals just as much as classical computing does. But there's a difference. So the second big difference today, quantum conditionals are hard to compile. And classical conditions are easy to compile. OK, so here's a classical condition. We have a conditional where the condition is B0 and B1. There's two booleans. And one way to compile this is we could make sort of a straightforward cascade of ifs. If the first boolean, then if the second boolean, and then we can do our thing. That gives, if you expand this to n conjuncts, you will get code of linear size, of course. And the overhead is very small to make this happen in machine code. For quantum, if you try to do a similar thing, you will end up with code of exponential size in n. And so that's not good. So that's already like a problem. So what can one do? So here comes just an example of one of the things one can do in quantum. Whenever you have an instruction in quantum, you can also have the square root of that instruction. And so I took the example from the previous page, and then I just rewrote it with q's instead of b. So now it looks more quantum-ish. We have a condition with q0 and q1. And then, so those are both qubits. And then I want to do an X gate on qubit number 2. And so we should not compile this to this cascade of ifs that I showed before. But what one could imagine is to do the following. Let's do like this linear sequence of ifs, where we do an if on the first qubit and an if on the second qubit. And then we get the idea of doing square root of x. And it's not a bad idea, because if both q0 and q1 are 0, then nothing will happen, which is correct. And if both q0 and q1 are 1, then each of those two ifs on the right will do square root of x on q2. And really what will happen is, after both these instructions go, we will have square root of x times square root of x, and we will have the net effect of x. So the point is they get multiplied together. A lot of stuff in quantum computing is about multiplication. However, the problem is that if q0 is 1 and q1 is 0, or the other way around, just one of them is 0, then we'll end up just doing square root of x one time. That's not good. That's neither here nor there. However, it turns out that one can fix this. And so that was something we were working on. So we take the same two instructions, and then we do a little trick. And I want to, let's call it a technique. That sounds much better. so we'll do something that I'll just go through just to give you a little bit of sense of how reasoning in quantum computing goes. So the table at the bottom is supposed to illustrate that this code works for all cases. So the first thing to know is that quantum computing is applied linear algebra, and so it means that all we need to work with are basis vectors. If we can show that everything works for basis vectors, it always works. And so in this case here, that turns out to mean that here, if you look at the first column at the bottom, that if we can look at Q0 and Q1 and just think about the cases 0, 0, 0, 1, 1, 0, 1, 1, we are good. If everything works for those 4 cases, linear algebra takes care of the rest. And then now comes the second point. I'm going to think of Q0 and Q1 as a binary number in, actually, it's like a binary number with 2 bits. So it's 0, 1, 2, 3, I guess one could say. That's how I'll think about it. Written in binary. And the least significant bit is Q0, and the most significant bit is Q1. And so then what I will actually do down here is that I'm going to write Q1 first. So when you see this 0, 0 here, it's actually first Q1 and then Q0. That'll just make all the reasoning go very nicely here. So this thing of using sort of binary notation for numbers, that happens all the time in quantum computing. So I had to get used to that at some point. So here we go. So we have these 5 lines of code, and you can see there are 5 columns for each one. And when we get to the last column, we have executed all of this code. So the trick that we are using here is that there's some +1, -1 going on, mod 4. So we're taking this 2-bit number, and we're going to do +1 and -1. And and then there's this last thing to note, which is you can see this is a dagger, square root dagger. That's quantum notation for inverse. So it's like going back. Instead of doing square root, we are kind of like taking away a square root. And so it goes as follows. So let's look at some cases. So 0, 0. So we just do like back of the envelope here. So we start with 0, 0. So both of the Q0 and Q1 are 0. Then if Q0 will do nothing, if Q1 will do nothing, then we will say Q1, Q0 +1. Well, so now we go from 0, 0, that's 0. +1 is 1. And so that means that the bit pattern is now 0, 1. Q1 is still 0, so that does nothing. And then we subtract, and we are back to our bit pattern from before. So absolutely nothing happened. And that's what you see here. We are in 0, 0. Another easy-ish case, but more interesting, is 1, 1. Let me go to that one. 1, 1 says, OK, now both the qubits are 1. So it means that we will do what I said before. If Q0 is 1, we do square root of x. If Q1 is 1, we do square root of x. Now we have done x. So that's why down here we land on x applied to Q2. So then comes the rest. So we add 1, modulo 4. So this bit pattern 1, 1 gets changed to 0, 0 after the mod 4 kicks in. And then at that point, both the qubits are 0. So if Q1 does nothing, and then we can subtract, and we get back to our bit pattern before, and the net effect was that we got an x. So we disturbed nothing. I added 3 lines of code, but it still works on the 2 cases that worked before. So that's good news. Now I will show one of the other 2 cases, and you will see that it's still, that now there's an improvement. So let's do this bit pattern 0, 1. So Q0 is 1, so we do square root of x. And then Q1 is still 0, so we do nothing. And then we do +1. So we get the bit pattern changed from 0, 1, which represents 1, to 1, 0, which represents 2. And so at that point, Q1 is 1. And then we take away 1 square root of x, and we are back to just Q2, and nothing happened. And so somehow this +1, -1 thing just solves all our problems, and it works beautifully for the case of 1, 0 as well. And so, so this works for the case of this conditional, and it turns out that it generalizes. And all this +1, -1 business can also be done in a way that is linear. And so we end up with linear code for this case. And just as an aside, I want to show you how a circuit can look. So here's a quantum circuit that does exactly what we had before. You can see we have some gates there. So you notice that I call the qubits A, B, and C. In this case, we have some gates here that touch 2 qubits. They all touch 2 qubits. In fact, some of them touch AC, some of them touch BC, and some of them touch AB. So they're all 2-qubit gates. But the key thing is that the scheme generalizes, and we end up with no less than 278 times n for a conditional with n, what is that? N conjuncts in the condition. That is a big number, and kind of depressing to think about is that the best known lower bound from the theoreticians is 2n. So there's a big gap there. But just to tell you, things used to be quite a lot worse. Until recently, Qiskit, which is IBM's open source software stack for quantum, would give you an exponential number of gates. So that's actually the green line here, where we kind of have the number of conjuncts on the x-axis and the total number of gates on the y-axis. If we go to the Nielsen and Chuang book from 2000, which is usually called the Bible of quantum computing, the best they had in that book was actually n squared number of gates. That's the yellow line here. As it happened 10 years ago, Craig Gidney published the first linear compilation algorithm. That's the red line here, and then finally we get what we have here. But you can see 278 times n, it's still a lot. IBM is now implementing our scheme, and it goes into Qiskit. So now, either now or very soon, you will get a linear number of gates when you use conditionals in Qiskit. The problem is that all this is no good for the new agenda for quantum computing, computer science research, because there's no error correction here. If we think in terms of the software stack, what we are doing is that we are compiling directly from a source level, quantum algorithm level conditional directly to the hardware gates. And there's no error correction in the middle. And so it means that if we are going to have real, honest-to-God, error-corrected conditionals, we need to figure out how to factor this through the intermediate representation and eventually get the whole software stack going. So there's a whole research agenda there. So we need more papers on quantum conditionals. All right, second point I want to bring up is optimization. So you know, Andrew Appel has the full employment theorem for compiler researchers. There's also a full employment theorem for quantum tools researchers. In this case, it goes as follows. The basic theorem is that if you give me a quantum circuit, for me to find out if that quantum circuit implements the identity function, does absolutely nothing, is QMA complete. QMA is the complexity class that's the quantum sister of NP complete. And so QMA complete is like harder than NP complete. And so what this implies is the corollary that both optimization and verification of quantum circuits is QMA hard. And that's the full employment theorem, because it means that now we can build optimizers and verifiers until the cows come home, and we can just keep improving them. And indeed, there are lots of quantum circuit optimizers out there. I listed eight of them here for 8 of my favorite ones. There are many more, and they are very interesting and different in interesting ways. The one I was working on is quartz, the one second from the bottom, and we had a particular angle on things that I want to talk about today, but there are many more angles on quantum optimization that are in these other tools that we don't cover. So our angle was to say, from math, we get identities between products of matrices, here written as circuit identities. So really what you see on each of these identities is a little product of matrices that's equal to another product of matrices. And now, once we have bunches of these, one can start to say, let's use them to optimize. So at the bottom here, I'm using some of the rules above, and one could say, well, so here we have a circuit with 4 gates as it is. That's how the count comes out. And then we could apply a rule, and we could apply another couple of rules, and then you can see over here we have only 3 gates. That's an improvement. We should just do more of that. And now it sounds intuitive that the more rules we have, the more we should be able to do. And so the idea we got in Quartz was, let's just generate all of them, all the rules. And so we set up the following generation scheme. What it does is to say we have this sort of syntactic idea of what an identity could look like between 2 matrix products, or two circuits. And let's just put down n, the number of qubits that we will deal with in this identity, and q, that would be the number of gates on each side of the equation. And let's just generate everything up to that size. And then whatever we generate, we will pass it through C3 to see if it's a valid identity. And if it is, now we have a lot of rules. And then in the pruning step down here, what we will do is we will prune away all the identities that are implied by some other identities and just like pare it down to a really core set that has no redundancy in it. And then once you have these rules, you can just feed them to the optimizer, and now hopefully there we got a lot of rules, and then the optimizer can do a really good job. Actually, yes, we get a lot of rules. Already up to 3 qubits, and this is for a particular set of gates, so this is how it works in quantum computing. You have to fix the gates that we can work with. You can either take the gate set from a particular quantum computer, or you can take the gate set that the theoreticians find interesting. And for a particular gate set here, we got for already up to 7 gates on each side of an equation with just 3 qubits in the picture, more than 300,000 transformations. And now the number of transformations is so big that now it becomes like a time problem for the compiler to go through them. There's just too many. And so the compiler will have to pick some. And now there's this whole sort of a follow-up line of research on how do you pick the best transformation. So one paper I know uses reinforcement learning to learn which transformations to use when. Very fruitful. I will just talk about the quartz results as we had them. And so what we did was that we used a very, by now, standard benchmark set from Matthew Amy and company from 10 years ago that many people use. There are 26 circuits in there, and we optimize. You can see how many gates are there, just to get a sense of we're trying to optimize the number of gates. And then we go through some different optimizer. Here's Qiskit, as straight up as it is from IBM. Then there's this paper from mainly from Maryland from 2018 that I think is a wonderful paper. Here's the Vox paper from POPL 2021 that did the first verified quantum compiler. And then we have the quartz results over here. And what we do is we add a little bit more than what I said. We also have some static analysis-based optimization that gives the first 19% of improvement. And then we add all these local rules with heuristics for picking some of them to optimize, and we get up to a 29% reduction in gates. And so that's what it is. But of course, there's no error correction in this picture at all. What we really need to do is to have an optimization story for a quantum software stack where the optimization of error correction gets special attention. And the reason why this is not just one more case of something general, it turns out that the software that we need for doing quantum error correction is actually a little bit specialized. It is very specialized in terms of the gates that it uses and the way that it works. And I think there are huge opportunities for optimization there that we just don't really think about when we try to optimize a general quantum circuit. And so we need to get good at that. So we have nothing like that. We need more papers on quantum optimization. Then let me move on and talk about optimality a little bit. So I showed you this circuit before, and it's actually optimal in a certain sense. I will tell you which sense. So what we have is a conditional. One can also write the conditional the way it is on the left, which is very compact. And what you see on the right are these 5 2-qubit gates. So 5 gates that each touch 2 qubits. And it turns out that if all we're interested in is to count 2-qubit gates, which is a good idea, because on a typical quantum computer, that's the slowest kind of gates. They're slower than the 1-qubit gates. 5 is what we need. You cannot do it with 4. And that was a theorem that came out in 10 years ago. Apparently, a lot happened 10 years ago. And that theorem was like 2.5 pages in a physics journal. That was a paper by Minxin Ying and Nenkung Yu. And I love that paper, and I decided I'm going to learn the proof. And so what happened there was that I found out about the paper on a Saturday, and I thought, oh, this is a quick proof of a beautiful theorem. I'm going to learn the proof, and then I'm going to give a lecture about it on Tuesday, because I'm a little short on lecture material for my class. Okay, so 100 or more 1-hour Zoom calls later with Nenkung, we finally had a write-up in LaTeX. And in our version, which we published in a math journal last year, it's 60 pages of LaTeX. And I'm showing you the structure of the proof here just to give you a sense that there's a lot going on. one could think that, oh, this is just like many, many cases that are all very similar, but it's like, no, there are only 2 cases in the proof, and everything is very different from everything else. My students formalized most of this proof in Coq, and it's 16,000 lines, building on top of Robert Rand's library of QuantumLib, which has a lot more lines in it. And so in total, there's a lot going on. And so what I got out of this is that there's a huge potential here for formalizing not just the quantum algorithms and the quantum compilers, but also some of the math that's underlying. And that I think is a quest that the whole verification part of the community can take up. But I also want to talk about optimality in a different way. Once we move down further towards the bottom of the software stack, we get to where the physical gates of the quantum computer live. And at that level, we have to realize that on some qubit technologies, you cannot do 2-qubit gates on any 2 qubits. There are restrictions. And I'm trying to illustrate the restrictions here. Oftentimes, you will find that there are 3 qubits you want to work with, and actually, even if they're quite close together, only 2 pairs are connected, and the 3rd pair isn't. And so you can imagine for my conditional where I'm using 3 qubits, this is like a pain, because this optimal circuit I showed is using both AB, AC, and BC. But then if you don't get all of them, what are you going to do? And so some programming comes in, and so I have this picture here where I focus on, suppose we can only do 2-qubit gates on A and C and B and C. And so then what we can do is we can program a little bit. And what I'm actually doing here is I'm taking the circuit that I had before, and then I'm saying, well, so now we cannot do AC. And the AC gate was sitting sort of here where I'm circling. And what I will do is I will insert 2 swap gates. That's the 2 funny ones with X connected here, some X is connected. And then I make some changes. And now what I have is a circuit that, if you just think about it for 2 minutes, does exactly what the circuit did before. But now what you see is, first of all, there are no gates that connect from A and C, from A to C, so that's good. And second, we have a couple of gates here that both work on B and C, and those could be combined. And so we are down to 1, 2, 3, 4, 5, 6 gates. And that's actually optimal. And so we took it upon ourselves to prove that is optimal. And now we actually built on this previous paper in terms of the proofs. And so now there's more stuff. And just to give you a sense of how this works, if you look at it from a particular angle, which is to say what we really need to focus on are 8x8 matrices that are diagonal. So that kind of represents a particular kind of operations that work on 3 qubits. In this case, it's a conditional on 3 qubits that we are interested in. Then it turns out that what you can do with 4 2-qubit gates that work on any combination of AB, AC, BC is just the same as you can do if you are restricted to 4 neighbor gates in terms of one of these 3 pictures that I showed, which is again the same as what you can do with 5 neighbor gates. And so one of the implications here is that it makes no difference whether you have 4 neighbor gates or 5 neighbor gates. You can do the same if what you want to do is implement a conditional in particular, which is kind of surprising, but that's how it goes. And so you can imagine, again, we're very suspicious about whether this was correct. And so there's this whole effort, again, to verify all of this in Coq to see that it works. And so I think there are many things like this that have a direct bearing on how we compile our things and what is the quantum theories that we build on. The more of that we can get verified, the better. And in particular, quantum error correction is going to explode in research over the next 5 years. And there will be so much new stuff there, new error correction techniques, new optimization techniques, and it will be very difficult to experiment with that and be confident. The right way to go is to verify that stuff. So we need a whole verification agenda there. That finishes my second point. And now I want to dwell on the point that this breakthrough in quantum error correction will bolster the computer science community. And I went to CS rankings, so thanks to Emery Berger, and simply looked up in the CS rankings conferences how many papers had quantum in the title. So it's not perfect. I know there are papers on quantum that don't have quantum in the title, but that was easy for me to do. And here's the count for 2020, 21, 22, 23, 24. So 5 full years, calendar years. And there are almost 700 papers represented here. And you can see it's growing. It's very clear that even until this breakthrough year of 2024, this is growing. And I fully expect that now it's going to grow more. I want to give you a little bit of a breakdown. So if we take these papers and look where the center of gravity is, the center of gravity is not so far away from programming languages. And most of the, I must say, the biggest chunk of papers are up towards the top of this picture. Theory, Fox, Soda, Stock. There are more than 100 papers the last 5 years that have quantum in the title. The hardware conferences, I think, naturally have many quantum papers because I think the hardware, to me, is like, that's as close as one gets to sort of the whole physics agenda that has been going for a long time. So both the design automation, DAC, had almost 100 papers. And then the more sort of architecture level, ASP+, ISCA, and so on, again, almost 100 papers. And then we get to crypto. So along with this agenda of advancing quantum computing and making quantum computing succeed, there's also the worry that one day it may succeed. And then what do we do with all the crypto when Shor's algorithm starts to work? And that's where the post-quantum crypto comes in. And you can see both crypto and Eurocrypt, many papers, again, almost 100 papers. That's one of the things they're working on there. And then for machine learning, it's actually quite natural that ICML and NeurIPS would have many papers because multiple reasons. One is quantum computing is applied linear algebra. A lot of machine learning is applied linear algebra. And so it seems like a match made in heaven to invent quantum machine learning. And there's a lot of people working on that. But second, of course, one could also imagine machine learning techniques that will help us make the software stack of quantum computing better. There's a lot of other work on that. And then we get to the programming languages. And as it happens, PLDI, POPL', and UPSLA have had an even smattering of quantum papers over the last 5 years. And you can see here figures prominently in this list. And I think that we are at the point where quantum computing is seeing now that quantum computer science will be more important to quantum computing. And I think that the agenda I'm outlining here will make programming languages very core to the next agenda for research in quantum computing here. I want to do a little bit of United States-centric stuff because that's where I live. There's a lot of investment going on. So there's a lot of national investment going on in other countries as well. I just want to touch on United States. Most recently, the National Science Foundation started the NQVL program last year. There are 11 projects. Those projects are 6 of them are in quantum computing, 3 of them are in quantum sensing, and 2 of them are in quantum networking. And they are all designed to be 8-year projects. So I'm outlining below how those 11 projects get some money in the first year, then they get down-selected, then they get more money in the next 2 years, and then they get down-selected again, and then they get even more money in the next 5 years. And say again? That's very strange. Can we complain to the AV people? Do you think the adapter has the problem? Oh. That's amazing. How is that possible?
It's a magic trick.
No, but now plug it in again, and then let's see. So that's very curious. So you should think that this is running quantum computing, but it isn't. So I can no longer change the slides here. So I can see the AV people are working hard back there. Hey.
We tried unplugging and replugging.
Yeah. Anyway, but let me tell you that the project I'm in is a project led by a physics professor at UCLA and with participation from Berkeley, from UCSD, from other places, and our industry partner is Continuum. And I guess our ultimate goal is after 8 years, we will produce a quantum computer with 60 logical qubits. And a lot of the research agenda is like the research agenda that I'm outlining here, that we need a software stack that has error correction in it, and that there are many problems to solve if we are going to get to 60 logical qubits. And what I see around the world is that there are these investments that are happening from national governments at a more regional level than the national government. I want to also add a little bit about, okay, so I have a picture of the mall. So that's a picture of the mall where the quantum research are going to move once they've done a little bit of refurbishing inside. But let me for a moment also talk to the education people in the audience, to the academics. So for me, this is not just a research agenda. In 2019, I was on my way to POPL. I ordered Minxin Ying's book. And on quantum computing, I came back, there was the book, I started reading, and the next day I sent email to all the people in my department saying, starting April 1st, I will teach a course on quantum computing. And that puts pressure on me, in particular because within an hour I got email from 2 of my colleagues saying, I have changed my schedule so I can attend your lectures. And so the next 2 months, I was learning quantum computing as fast as I could. And by now, I have two courses in a sequence, Quantum 1 and Quantum 2. I call it Quantum Programming and Quantum Algorithms, 10 weeks, each of them. And more than 450 students have gone through quantum programming, and more than 130 students have then stayed on and taken quantum algorithms. And it's wonderful. So it's a wonderful experience with just hearing all the different backgrounds and knowledge that people have. And in particular, because we also started this quantum science degree, which is housed in physics, but also has participation from computer science, particularly from me. It means that I have students in the class from certainly computer science and physics and math and chemistry and some engineering departments. And it's just wonderful with all this background. And it makes for an interesting challenge of communicating with all these people about the technicalities of quantum. And then one last thing. Some of us are trying to convince the National Science Foundation to start a program in computer science with money for quantum research. And to that end, we are planning a workshop in the late summer where the goal is to write down a computer science research agenda for quantum for the next 5 or 10 years. And I hope that some of you will be able to attend. And if you want to, please talk to me. And so that brings me to the end. So here's my research agenda. I believe that computer science research, that we are starting to near critical mass, where we can submit and publish our papers in computer science venues, have our papers reviewed by our peers, where we have enough critical mass that a computer science paper can get reviewed by computer science experts on quantum. And then we have a whole agenda in front of us, which I think is going to create a lot more energy for the computer science people working on quantum computing. And I think that together we can advance the timeline and make quantum computing succeed sooner than it would otherwise. Thank you.
Thank you for the talk. We have plenty of time for questions.
Thank you for the great talk, Jens. In my personal experience, working in this area benefits from, if not requires, communicating with theorists, devices people, architects, a whole lot of people that PL folks might have some language barriers with. How do you think that as a community we can overcome this and make sure that we're always working on relevant and timely topics?
I think that the language barrier is real, and I certainly experience it in my teaching. But I also, because of the collaborations I'm in, I get to talk to physics people and chemistry people all the time, and the language barrier is there. And it's not just talking, but it's also reading the papers that, for example, come out of physics. They're written in what I would say, it's written in a different way. And it takes time to just get in and understand that they're making assumptions that is known to everyone in physics, but they're not known to me. And so I think, as with all other collaborations that are interdisciplinary, this thing of getting together and staying together, that's the key. And take the time to talk long enough that a common vocabulary emerges. That, I think, is the key. And so I have had the good fortune to, for example, get involved in the largest quantum computing research center in the United States, which is housed at Berkeley. It's run by a person in physics, but they somehow took me on board 5 years ago, and we have been able to just keep talking. And I start to learn what they're saying, and maybe they start to learn a little bit what I'm saying, and we can do things together. So getting together and staying together is the key.
Couldn't agree more. Let's do more of that. Thanks.
So I've been trying to relate the examples you're showing us to classical examples to understand better how we think about optimization here. What you told us about seems to be focused on kind of an analog of improving area of a classical circuit.
Okay.
But a big concern for classical circuits is parallelism and reducing the length of the longest sequential chain, which you didn't mention here.
Right.
Is that also a concern in this domain?
It is a concern, but I think that it is beginning to be less of a concern for the reason that when quantum error correction starts to work, then decoherence, which sort of threatens to just put a full stop to quantum at some point, starts to be less of a concern because decoherence just becomes one more error that error correction is supposed to deal with. So I would say that the raw number of gates is beginning to be more of a concern than the just actual depth of the circuit. Every time we execute a gate, it introduces errors that have to be corrected.
There isn't a concern with reducing the latency of getting the final answer back?
Oh, that is a good question. So I think that we are always interested in time to compute. But given all the other problems in quantum computing, I think that that's sort of a little bit down the list of priorities, but that is always a concern. Anyone who can do worst case execution time for quantum computing, that will be super welcome.
And when the community gets to working on that, will it look like trying to create more parallel classical circuits in some sense?
I think that parallelism really for these quantum circuits that I draw is simply a matter of gates that are sort of stacked on top of each other. And the more we can do of that, the better. And indeed, I remember yesterday I was just online in my class, being here in Denver, giving a talk about Hamiltonian simulation, about simulation of physics. And there's a very nice case there where it looks like the depth will be very big, but just with a little bit of human smartness, you can make the depth almost nothing. If we can get compilers to automate that, wonderful.
Thank you.
Your presentation of like how quantum error correction interacts with these algorithms, you said it was a sort of a software problem, and I was thinking that this would come out sort of similar to how concurrency is treated in modern classical computing, where it's now partially the source level, user program level concern. It's not something that we can just ignore and hope that the compiler solves it for us. But here, this pipeline is still separating the concerns of quantum error correction into a layer of the stack, and then we're just programming something for the logical qubits at the user level. Do you think that this could be improved by like having the, divesting some of the responsibility for doing error correction, or at least error correction friendly techniques to the programmer?
I understand. It's a very good point, and I like the summary very much. I have two or maybe three things I want to say. The first is, I think that we are sort of in this sort of same dreamland as concurrency was 30 years ago, where the dream was that you write your sequential program and the compiler makes everything nice and parallel and much faster. And then it turns out that it's not always so easy, and the programmer has to get more involved. I think that we may very well one day end up in what you're saying is that this dream of writing the software stack this way doesn't quite give us everything we want, and we need the programmer to be more involved in saying something about where the error correction goes. The second point is that maybe we should go further than what you're saying. People are talking about hardware-software co-design in this whole quantum area, where maybe we should go all the way and look at how the qubits are architected together, what is connected to what, because if you do it this way, it's great for this algorithm. If you do it this way, it's great for that algorithm. And then it's even more aggressive programmer involvement than what you're saying. I think there's going to be a lot of work in these directions the next 10 years.
Jens, thanks for a wonderful talk. This is Kedar Namjoshi from Bell Labs. So I want to actually go back to the hardware. So I get your point about the software, and computer science being important. But if you think back to the history of classical computing, hardware in the 1950s was very error prone to the extent that, John von Neumann wrote this classic paper on how to build reliable systems out of unreliable components. So my question is sort of, where is the hardware going? Like, is it getting, significantly better at reducing faults? And the second question is, do the physicists have something like the Shannon theorem that says you can't get beyond a certain point? You can't sort of reduce are there sort of fundamental limits on how low the error can get?
Very good. Excellent point. So let's see. So two things. So the first is, so clearly we can hope for better physical qubits with lower error rate. And my understanding is that the quantum computers are getting better and better on that front. Most recently, we saw the announcement Google have this new Willow chip, which is very, very good and has a very low error rate compared to some previous ones. And so that is saying that clearly when the physical qubits get better, we may either have the error correction algorithms that we had in mind do even better, or we may need less error correction to get to the same endpoint that we had in mind. And so in that sense, I think error correction and better physical qubits are just working hand in hand. And so the physics people are working over there, and the computer science people can work over here, and it's synergy. The second point about whether there's a limit, I actually don't know. So here my knowledge of physics ends, and I cannot give the answer. And I hope that there will be physics people that can fill that in at some point.
I have a quick question. You had a square root, and that makes me nervous.
Yeah.
So do quantum computers manipulate reals or some kind of clones?
Very good. So quantum computing manipulates a vector of complex numbers. And so the state...
Number, they are built out of reals? Or?
Yes, the complex numbers build out of reals, for sure. And so I managed to sort of hide this under the hood the whole talk. But the state vector of a quantum computer is a unit vector of complex numbers. And each individual step of the quantum computer, all it does is to take you from one unit vector of complex numbers to another unit vector of complex numbers. It's a very long unit vector, because if you have n qubits, you actually have 2 to the n complex numbers. And so if you had 300 qubits, which some quantum computers today already have, you have 2 to the 300 complex numbers, which is more complex numbers than there are atoms in the known universe. And so it's just like very long unit vectors. And, but back to the square roots, because we have complex numbers, we can do square roots. Complex numbers have square roots, and matrices built out of complex numbers have square roots. Everything is very flexible there.
What do you think?
Testing.
7 assistants to ask my question here. What do you think the societal consequences will be of succeeding in this endeavor? And why aren't you concerned about those, or how do you think we'll mitigate them? And do I really want to be involved in this enterprise?
Very, very good. So I will just outline a bit of what the overall hope for the quantum computing area is. I would say that when we go to the physics simulation, the areas that will benefit from that will be material science, chemistry, also some basic physics, where they want to design new materials or design better batteries or design better things where you really need to be working at the atomic level, and where more computing would be better, where people are essentially just hemmed in by that they don't have enough computing power with classical computers, and they would be able to do more and better designs if they had quantum computers. The second one is, of course, Shor's algorithm, which is, in the first story is kind of happy. The second, the Shor's algorithm, that's kind of a sad story, because that will mean that you can read my credit card. And you'll just break the crypto when I access the bank, and then it's not good. So that's kind of a sad story, and that's why we need post-quantum crypto. to be sure that if quantum computing succeeds, then we have something going on. But I think that as an intellectual endeavor of even making Shaw's algorithm run and run on integers we cannot factor today, that's still a good intellectual endeavor, but just a little bit of a sad outcome.
All right, with that, let's thank Jens again and move to the coffee break.
Thank you. Thank you.
Can you project the slides?
Session on compilers and synthesis. Our first talk is about MIMIR, an extensible and type-safe intermediate representation for the DSL age by Roland Leysa.
Yeah, thank you so much. My mic? All right. Yeah, so I'm Roland from University of Mannheim. I'm moving soon to Göttingen. I'm having an open position for PhD students. If you're interested, reached out to me. And this is a joint collaboration with Marcel, Joachim, and Sebastian from Saarland University, who are also around here. All right, so let's jump into it. So domain-specific languages, or DSLs, are nowadays everywhere, whether you want to have a query to your database system, this is a DSL, or cool shader effects in your graphics system with GLSL or so, these are also domain-specific languages. Or if you're configuring your firewall with IP tables, it's also DSL, or nowadays with all those fancy tensor frameworks like PyTorch, XLA, JAX for machine learning, these are also examples of domain-specific languages. And at least if you're a business of doing high-performance domain-specific languages, the reason why we want to have that is that we want to optimize beyond typical library boundaries, right? So let's suppose we have a super efficient matrix multiplication implementation in our back pocket, but still if we aren't able to figure out that a matrix M multiplies by 0 matrix is 0 and M multiplies by the identity matrix is M, or how to reorder a chain of matrix multiplications to come up with a minimal number of optimizations, we are still losing in these examples, right? So this is one of the most important reasons why we want to have high-performance domain-specific languages. Now we have like this whole zoo of DSLs, and yeah, it's sooner or later we want those domain-specific languages to interact or maybe build upon each other. So for example, if you're writing a tensor DSL with matrix multiplications and all sorts of tensor operations, you probably want to do machine learning, and then you need some sort of compiler passes that computes the derivative of your program, and this kind of needs to interact with the tensor computations. When you've done all that, you probably don't want to go straight to low-level code. You're probably lowering it first to, let's say, affine loop nest or so, and then you're going down to something even more low-level, and depending on whether you're compiling for CPU or GPU, you probably need a whole different set of primitive operations here. You can see how, one example, how those DSLs on different abstractions level kind of interact or build upon each other. Now, the biggest kid in town to do this right now is the multi-level intermediate representation, MLIR. And what you do here, you can define what they call dialects, right? And those dialects are kind of domain-specific program representations, for example, for computing tensors. Now what you're doing with MLIR, you define what they call ops. And those ops can be, for example, matrix multiplication or other operations. And MLIR has a very syntactic approach to pulling this off. This means that you also have to extend the parser of MLIR in C++. Also, those ops are not first-class citizens. This also means you have to extend the type system of MLIR in C++. Now doing this for a whole bunch of plugins, and then you have, or dialects, how they're calling this, and then you have like this whole zoo of different dialects, and if each one of those things has its own type system, this raises serious concerns about the safety and soundness what you are doing there, right? So MLIR had a vast impact in the compiler community, but it also has some limitations. So, for example, it only has limited support for higher order functions and doesn't support polymorphism or dependent types. Now, what we came up with, Mimir, is designed in a different way. So we're trying to achieve a similar goal, all right? So Mimir is a compiler intermediate representation. It's just a program graph in the style of a sea of nodes. I will come back to that in a minute, what that means. And at its core, Mimir is a typed lambda calculus based on calculus construction pure type system. And Mimir also has a textual interface called MIM that I'm going to show you some examples of. Now, what you're doing when you want to have your own domain-specific program representations, you're defining what we call plugins. And what you're doing there, you're simply declaring functions, for example, matrix multiplication or things like that. And those things are first-class citizens, so they simply have a function type, but they don't have yet an implementation. For this reason, we don't need to extend the parser of Mimir, MIM in any way. And also, they have a type, which is rooted in this Mimir's type system. So you also don't have to extend the type system of those plugins in any way. OK, so let's jump to an example. Here you can see a small example of a tensor interface that I'm specifying here in MIM. So first, if you're doing matrix multiplication, we first want to define what a ring is. So ring needs an element type T, a zero element, addition, and a multiplication. And now we have this matmul operation. So this is what we call an axiom. So we are declaring a function here with this signature. So this matmul operation is polymorphic over this ring that we just defined. Then it receives 3 dimensions, M, L, M, N. And then we expect an L times M array. So this is what those quote signs mean. This is an array and an M times N array. And it spits out an L times N array. And we are grabbing from this ring the element type T. So this is an extraction operation. And along those lines, we can define all kinds of axioms or domain-specific optimizations. So this is the interface of the plugin we're declaring here. And then we need an implementation to do other more sophisticated things. For example, normalizations like matrix times 0 is 0, these kind of things. And maybe more sophisticated optimization passes, like, for example, reassociating matrix chain multiplication, or lowering passes that looks for this matmul calls and lowers that then to something, to an actual implementation, like a low-level loop nest, or maybe calling a blast routine. Okay, so once we have that, we can now go ahead and use our small domain-specific plugin that we've written here. So we are loading our plugin here, and all the compiler transformations, whatnot, will be loaded into the Mimir compiler. And now we want to multiply 3 matrices. So we are invoking tensor matmul with some ring, and we are applying mul to A, B, and C. And this is the actual compiler intermediate representation that you will get from that. And this is the data structure you're working with in the Mimir compiler to analyze and manipulate the program representation. So what you can see here, here's the application that expects 2 matrices B and C. And the callee is here this curried call of this matmul axiom that we specified. And here we have the other multiplication that receives this thing as right input and A as left input. And you can see it points to the same curried call of this matmul axiom that we defined here. So this is why it's called a C of node. All those operations are just held by data dependencies. And and that's it. In addition, every node has one edge that points to its type. So I already mentioned the type system of Mimir is based on pure type system, pure calculus of construction. This means that there is no syntactic category for types. Everything is an expression, even types. Let's have a look at the actual intermediate representation. We have functions, right? Functions can be recursive. So we're supporting full recursion here. We have dependent function types, and we have application. Let's see how the graph snippet, so to say, will look like. So this should be fairly familiar with you. We also have tuples and arrays. We've already seen the tuple type in the example with the ring, and we extended dependent pair types to n-ary dependent tuple types. So you can have any number of elements here, and all those elements may depend on the values of the preceding elements. You also see this here in this graph, right? We've also already seen the arrays. Arrays may also be dependent, so the element type may depend on the index this thing is sitting on. We have tuples, and we have extraction. In order to make extraction type safe, we're not going ahead and simply extracting from a tuple or an array with any kind of index, but instead what you need, in order to extract from a 3 tuple, you need an index of type index 3. Okay? And so these 3 guys here are inhabitants, the only 3 inhabitants of the type index 3. But also if you have an array with some unknown bound n, and you want to extract something from this array, this index I here must also be of type index n, otherwise this is a type error. Okay. So whenever you construct an expression in Mimir, those constructors are are smart in the sense that they are immediately try to simplify the representation. We're doing this for 2 things. First, they're kind of like low-hanging fruits for optimization. And second, we also need this for type checking. Coming back to that in a minute. Okay, so for example, whenever you have a tuple, and you're extracting with some constant, you will immediately receive the result here, and Mimir will never ever even construct this thing here. Another thing what we are doing, you're wondering, okay, we have tuples and we have arrays, but there's only one extraction operation, and the reason for this is because Mimir kind of blurs the line between tuples and arrays. So for example, if we have a homogeneous tuple, Mimir will normalize that to an array type. If we have a parametric array, Mimir will expand that to this tuple type here. And also, we are consistently removing one tuplet from the intermediate representation. These are just a few of the things we are doing here. Now, plugins can introduce their own normalization rules. Typical things that you want to do is implement things like constant folding, that 3 plus 4 is 7, or maybe various arithmetic simplifications that x plus 0 is x, or matrix times identity is matrix, these kind of things. As I already mentioned, these normalizations are low-hanging fruits for optimization. That's also important for type checking. We've already seen that we are normalizing array types and tuple types and vice versa. But also, since Mimir is a dependent type system, it may very well be the case that you have a type constructor T, and in this type constructor you have some arbitrary expression. And then you're in the situation sometimes that you have this expression here and this other variable that goes into that has this type, and they look slightly differently, and usually a dependent type checker are very picky about that, and then this program wouldn't type. Due to the normalizations happening, in this case, both expressions normalize to n plus x, and then this type checks again. I already mentioned that Mimir features full recursion, and if you have dependent type checking with full recursion, you're running into problems that this is undecidable. And the answer Mimir gives to that is that we allow partial valuation. So let me give you an example. Here we have a function f that expects something that expects an n and an array with n times n elements. And here we have y, which is an array with n by the power of 3 elements. And as written, this wouldn't type because n by the power of 3 is different than n times n. Now what we're doing here, we are annotating this function call with a so-called filter that instructs Mimir to better reduce this function call if the exponent of this power function is known at compile time. And this has the effect that this thing here will expand to n times n, and then this type checks again. Okay, so we've proven the progress and preservation in ROC for the core calculus. If you're introducing your own custom axiom and normalizers, so normalizers could violate preservation. For example, if you have this nonsensical normalization rule, 3 plus 5 to unit, this would then result in a type error after the normalization have been triggered. Custom axioms may also violate progress. So for example, here I'm bit casting 5 to index 3, which is obviously nonsense, or if I'm loading from a dangling pointer. So this may be intentional. If you're compiling an unsafe language, you obviously need unsafe operations. If you want to have a type-safe plugin, you have to make sure that you don't violate preservation and that the functions, the axioms you're using there are total and don't violate progress. If you're going down more low level, you want to talk about unstructured control flow, Mimir can also do that. We have continuations. Continuations are simply functions that don't return. So as a syntactic sugar, a function type whose codomain is bottom is a continuation, right? Or we write continuation of this thing if the return type is simply bottom. And this allows us to model arbitrary control flow. In this example, I'm kind of crafting an if diamond, how you would do that in a more classic compiler representation like LVM or MLIR. And this pretty much resembles CFG in SSA form. So you can do that as well. One interesting thing is that many optimizations you want to do, especially in this high performance setting, can actually be expressed as specializations. So for example, let's say you're dealing with some low-level code and you want to construct an unrolled loop. So what you do in LVM or MLIR, you would write a C++ program that constructs this unrolled loop. But what you can do in Mimir, you can actually write down a polymorphic current continuation where that is polymorphic over the accumulator type A, and it expects the number of iterations n. Here we're using this filter again, so if the number of iterations n is statically known, please unroll this whole loop. And now if we invoke this function, Mimir will automatically unroll the whole loop for us. We already developed several plugins, and what we did in our evaluation, check the paper for the details, we wanted to show that we achieve high performance, is expressive enough to host a variety of domain-specific languages, and that this enables us an interaction reusability of the plugins that we came up with. We have written, for example, 3 low-level plugins, pretty much in the spirit of LVM, and this allows us to compile Mimir to LVM using those 3 plugins. If we have something more high-level, for example, we implemented a plugin for regular expression matching, and this compiles down to those things. We show in our paper that the performance of this records matcher is on par with other popular regular expression engines, or we implemented a tensor DSL for tensor manipulation and a plugin for automatic differentiation. If you're doing things like backpropagation, we're lowering this to a plugin which can represent affine loop nest, and then we are going to the more low-level representation. Okay, so this is what we got here. Mimir is an extensible compiler intermediate representation. It's a type lambda calculus. You're finding the interface here. Then you come up with all those different optimizations and bundle that in one compiler.
Great, thank you. We have a couple minutes for questions.
Your type system seems very similar to the type system of modules in OCaml.
So in OCaml, it doesn't have dependent types, right?
It depends, yeah. But the only difference I saw was for arrays, but otherwise it looks very similar.
Yeah, it is very similar. So as I already mentioned, it's based on the calculus construction, pure type system. So all programming languages that come out from this area, obviously they are similar.
And they have functors and so on.
Yeah.
Okay. Who wants to ask a question? I'm sure you have a question.
Sure. To follow up, it's proof that you can encode ML type system in system F omega, and we are a superset basically of system F omega. Yeah.
Maybe a quick question for me about the automatic differentiation plugin.
Yes.
So there's a difference between exposing automatic differentiation as a sort of a whole program transformation versus an operation in the language. And it seemed like your plugin that that can be maybe applied multiple times to get higher order derivatives and things like that. Does your sort of plugin system that encodes these things as axioms with types in the language sort of imply that you need to implement it within the language as opposed to some button that you press outside of the language?
So there are 2 things at play here. So first, you're exposing this automatic differentiation as a higher order function, as an axiom. So you're kind of tagging, okay, so here's this function that I want to derive. Putting this into this AD function, and then gives you the derivative. And then, of course, there's inside of the implementation a path that goes over that and does the magic for you, right? So this is the magic button you're asking for. But also the compiler passes that you're implementing are exposed inside in this interface. You're writing something, okay, I have this automatic differentiation path of type compiler path, and then you kind of plug into your compilation pipeline.
Thing, axiom in the language, does the compiler have to support nested applications of it and things like that?
Yeah.
Thank you. Okay, great. Can we thank the speaker again? And get the next speaker. Okay, thanks. Our next talk
model with refinement calculus. So as is known to all, the generative AI helps programming a lot, and there are multiple industrial products in generative AI and programming, like Copilot, ChatGPT, and Cursor. And we also see many applications in generative AI on theory improvers that translate the informal models to a formal data. And we use the GPT model, Lindojo, and the Copilot that helps the theory improvers. But there's remain a big question is that the GPT suffers the hallucination problems. So hallucination means that it generates plausible information but incorrect. So for example, a very basic algorithm like find a square root algorithm, the GPT-4 will generate a algorithm like that, and it will also generate the test case and test it online and say that it all gets passed. But it still remains a question whether this is a correct algorithms. It generates the test cases and persuade you that the code is correct. But if you look details, for example, you test the find square root of 5.1, it will go to an infinite loop. So if we go deeper about the algorithm, you can find that the x plus n divided by x is actually have a graph of this kind of shape. So when x is small, it goes to an infinite, and when x goes to large, it also goes to infinite, and the minimum number would goes to x equals to square root of x equals to square root of n. However, the x, because the guard combination is x squared larger than n, which means the x equals square root of n is hard to get. So in real world, because of the float precision error, so many test cases can be passed, but mathematically it is actually a wrong code, and in some test case it will go to infinite loop. So how we can give a correctness guarantee on the LLM generated code? So we borrow the idea from the program refinement calculus, the Carl Morgan's versions. So the verifiable transformation of an abstract high-level formal specification into a concrete low-level executable program. So the previous square root example can have a formal specification like one precondition that for all input n such is larger than 0, and we want to find the x such that x squared is equals to n. So we can first go into a very simple example that we first find x such that x squared is larger or equal to n. So based on this precondition and the postcondition, there's many ways. And the large language model generates multiple code for that. For example, x equals to 1 equals to n equals to n plus 1. So we can find that some code is correct, can be verified by the automatic theory improver, but some can't. But formally, we can find that the x should be larger or equal to n plus 1/4. In that case, the x squared would be larger than n for all input n. And we can also verify that some algorithm like if n larger than 1, we can assign x equals to n, else we can assign x equals to 1. This is also a correct code, and it can be verified. So if we call back to the code large language model, so we consider the generated code from the refinement logic, we can find that the generated code by GPT-4 is just follow this idea that when n is larger or equal to 0, it assigns x equals to n if n larger than 1, else 1. So in that case, we can have a post condition that the x squared is larger or equal to n. So how we can get the final post condition that is x squared equal to n? So we can split the post condition like x squared larger than n and x squared less than n. So we can find a clear structure of while loop that we first preserve the invariant x squared larger than or equal to n, and then we want to get a state that x squared also less or equal to n. So based on that, we can build the invariant and variant and build the while loop with the guard conditions. And the next question is whether the iteration is correct, whether we can terminate the iterations. So we have 3 conditions of the iteration. The first is that the invariant preserves. So that means the new x always preserves the invariant x squared larger than or equal to n. So we can verify it. And the next condition is that the variant is decreasing, which means the progress x minus this new x should be larger than 0. So which means the new x is always decreasing. And it also can be verified. So the last question is whether it can be terminated. So as I talked before, because the x squared is larger than n, so the new x is always larger or equal to n, which means the new x is always satisfy this while loop condition. So it will never terminate. So which means the program is incorrect. So a simple fix is that we just say we should not have a fixed point of x. The new x should always not equal to the original x. We want the x change. So that's the best we can get for the x. So our assumption is that the LLMs have good ability in program synthesis, in guess the code. So we try to find some ways, some formal systems to verify the generated code is correct. So for example, we can give the LLM with the precondition and the postcondition and let the LLM generate or guess the code. Then we can verify it, whether it is correct or not. So basically, we can guide the LLM with very basic laws. For example, the skip laws. If the precondition just implies the postcondition, it's just a skip. So if we can assign x as a variable x with an expression that makes the precondition implies the postcondition, we can just assign the variables. So it also has iteration, alternation, and the sequential composition laws to build the programs and to guide the LLM to generate the code. So for example, still the square root algorithm, we have a formal specification that we now have an error bound E. So we want to find an x such that x squared is less or equal to n and x plus e squared is larger than n. So basically, we can split the postcondition into two parts. The one part is the invariant and the one part is the variant. That is the negative of the guard condition of the while loop. So in the first part, we can just first satisfy the invariant, which assign x with n plus 1. And then we can build the iteration with the guard condition that is negative this kind of condition and build the loop. Then we can try to verify whether this loop is correct. So this is incorrect because when x is very small, x is very small, for example, x equals to e fourths, which means the new x equals to negative 3 e fourths. So the x squared is actually increasing, so it will not terminate the loop. It is incorrect answers. So when we get an incorrect answer, we will have a fail feedback algorithm. So sometimes the ATP will generate some counterexamples to guide the LLM. Sometimes it will not, so the LLM will choose another direction to refine the specifications. So for example here, now the new invariant is x squared less than, which means we use this part as an invariant and the next part as a variant. So we can build the square root algorithm in a naive way. So we can also use another direction of refinement to build the square root algorithm with the binary search algorithm. We can say that we settle the upper bound and the lower bound with x, y, and first assign the lower bound and upper bound x, y, and gradually decrease the distance between the x and y, and finally achieve the guard condition. So we can reconsider these refinement laws. We will find that a big problem is that when we ask the LLM to find a sequential composition law, that means we want to find an intermediate condition to pave the ways for the future refinement. It was quite flexible. So the different laws have different flexibility. For example, the skip law is quite restricted. It must ask the precondition implies the postcondition. But for the sequential composition law, so it's not many constraints for this using this law. So a big problem is that how we can guide the LLM to utilize the sequential law correctly. So we inspired by the machine learning idea, so we learning the more advanced law from the data to make the formal system dynamically evolving. So remember, we have the different directions of refinement of square root algorithms. We can first assign the x equals to 0 that satisfies this kind of invariant. We can also use another direction that satisfies this part of post-condition. So in this pathway, there's many data that follow the same pattern. First, utilize the sequential composition law, and then initialize the variant to initialize the variable to satisfy the invariant, and then build the iteration law. And the specification would also follow the similar patterns. So we can gather them and build a new law. Maybe we can call it initialize iteration law that first satisfies the invariant, and then we go to build the while loop to do the further post conditions. So the correctness of this new law can be constructed by construction, which means we can build upon the basic law like sequential composition law, assign law, and iteration law. So we can raise example for the learned refined laws. So for example, for the traverse law for the irregular structures, so initially, if we want to tackle some array structure, we need to first set the first element as the invariant and gradually increase one. And this can be many steps, and you need to interact with many times. But we can then combine them together. That means we first initialize the variant, and we also set the iterations, and then also set the variant that is decreasing. So which means we can say that we only to have the next refinement on the PLI to PI plus 1. So for example, for the sort algorithms, so we can first define the formal specification of the sorted algorithm that we have a list such as this is a swap allowed list, and we want for all I, for all j in a range that Li always less than or equal to Lj. So we can directly use the traverse law to refine these specifications. And after use 2 times of traverse law, we can just remain the Li less than Lj. So then we can use the alternation law. If the Li less than Lj, which means we don't need to change the order. It's just the precondition imply the post-condition. We can just skip. If not, we just swap the element, and then we can get the basic sort algorithm, the bubble sort. So similar for the quick sort. So the quick sort is to find a k such that all the elements before the k is the sorted list, and all the elements after the k is the sorted list, and all the elements before the k is less than all the elements after the k. So we can just build a specification and refine them step by step. And with the advanced law, we can save a lot of time for refinement and proof. So the overall system is like, we first have an input that is human involved to generate correct formal specifications. And there's also many work in auto-formalization that interact with LLM to generate formal specifications. And then with this formal specification, we will choose a law by LLM and generate the corresponding code. And based on the code and the law, we will use the refinement module to generate the constraints to verify the code. We will use the automatic theorem provers with some SMT solvers to formally verify the code. If the code is failed to verify, we will send the feedback to the LLM to generate another code. But if it always fails, it will change it to a new law. And we will refine it until all the specifications get refined. So our program language is kept simple because the larger models is mostly familiar with Python. And our specification language also follows the Cork language. So we also have a specification building part because the specification may be complex, so we can split the specification top down to some small specification and refine them one by one and construct program bottom up. And we also use some real-world examples to instruct tuning LLM with the refinement and the laws. So our results show that we can save much time and pass more test case, and we can show a more robust code because with ever plus data set that is have more test case, we will not decrease the pass rate. So the limitation is that because we have a combination of specification, refinement calculus, ATPs, and LLMs, so we basically try to, based on the LLM, to build correctness guarantees for the LLM generated code. But sometimes there are some components maybe not that good. We need to make some pattern for the ATPs to verify the code. And another problem is that we didn't have quantified the optimization problem. So we only try to synthesize algorithm, but not synthesize or optimize algorithms. There are many paths from the precondition to postcondition, but we didn't quite quantify which path is the best way. So in a summary, so basically we build a sophisticated formal engine to powered by the strong LLMs to automate the formal task, like the program synthesis. So that's all for my talk. Thank you.
Thank you for the talk. This is very interesting. One question that I had, probably taking a step back, is I guess finding the invariant and the variant is probably one of the most important things, right? So how are you going about it? I see that you've applied it on like the square root algorithm, the binary search quicksort, and all these algorithms. So if I had some other naive algorithm, how would I go about solving this problem?
You mean how to find the invariant and the variant?
Yes.
Yeah, because for example, in some cases the specifications contain the is a conjecture form, so you can select one as the invariant and others as a variant. And you can also let the generate the invariant and use the ATPs to verify whether it is the strengthened postcondition or weakest preconditions. You can also verify whether the invariant is correct or not.
So the language model is generating the invariant?
Yeah, the language model also can generate the invariant and the variant.
Okay, but okay. All right, maybe I can ask that question. Thank you.
Great. Let's thank, yeah, there's maybe time for one more question.
Again, thanks for the talk. One thing I'm not sure I totally understood, there you mentioned very briefly you had a slide about finding new laws for different data structures like the array. You had this traverse law. Are these laws you're kind of dynamically creating as part of the loop of inferring a program, or are they things you have to provide to power the inference right from the start?
So we dynamically involve the system. So after we have 100 examples, check how much patterns in these examples, and then we create a new law for that. Maybe some typical patterns we can find from the laws. Yeah.
And does that require human intervention, or that's all done automatically?
It still need a human invention. Yeah, it will give some patterns, but you need to build the laws. I mean, you need to build the code for the laws. Yeah.
That makes sense. Thank you.
Thank you. Let's thank the speaker again. Our next talk is a remote talk.
One, two. Is that someone? Okay. Doesn't seem to work. an additional function that does not follow the original calling convention. So you are changing calling conventions. And to reason about that, we introduce what we called abstract protocols that materializes as an additional parameter in the simulation, in the relation. And we'll see in a moment how this can be used, particularly how this rule can be used. All right, so this is our methodology. Now, unfortunately, I don't have time to show the whole proof, but I have time to show the core of it. So I claim that the core of the proof is these two specifications. So the specification of the direct transformation and the DPS transformation. So the question is, what do we put here in these pre and post conditions? So for the direct transformation, this is straightforward. We just said that given two related similar values, calling mapd in both programs will yield similar values. So two functions return similar values, right? And this rule, this specification is actually a specialized version of a marginal reasoning rule in the logic that we can see here, and that is stated more generally for any function. So now, let's see about the DPS transformation. For DPS transformation, as I've said, we change the calling convention. So in the specification, we said the following. We said that given two similar input values and the ownership in the target program of the destination, so given all this, map and map DPS in the source and target programs compute the same thing, the same values, and additionally, instead of directly returning it, map DPS writes it in the destination. So this is basically the essence of destination passing style. All right, and as before, this specification is can be derived from a more general rule in the logic that I have produced here, and actually both the former rel-dir rule and this new rel-dps rule, both of these rules are actually derived from a more general rule that I've introduced earlier, that is the rel protocol rule. And this rule allows to apply a protocol where a protocol basically represents a change of calling convention. Right. So in our case, in the TMC transformation, we instantiate this Chi protocol just by basically rephrasing the two specifications. So conceptually, this is much like, this is essentially a co-induction hypothesis that is built in, that is internalized in the relation. All right. Now, I must also say that in the paper, you can also find other transformations that fit in this framework, that can be verified using protocols, so basically using this rule. And particularly, you will find the proof of an APS, accurator passing style transformation, as well as an inline transformation. To conclude, we have implemented the TMC, the tail module constructor transformation in the OCaml compiler. We have verified its soundness using relational separation logic. And we verified other transformations using abstract protocols. Thank you.
Before lunch, anyone has a question?
Hi, thanks for the talk. So similarities is a logic for concurrent refinement, and your language is sequential, if I understand correctly. Was that a problem? Did you just use the concurrent thing and ignored concurrency and it was fine, or did you have to do something there?
Indeed, it is sequential. We did not introduce concurrency, so say the full power of similaris, because basically we wanted to just capture the essence of TMC. And TMC, tail module constructor, the transformation, does not involve any trick aspects regarding concurrency, I think. So we've not used concurrency. And I don't think this is, I mean, I think we could just add it in the framework just as Similaris did, and there wouldn't be any particular issue, I think.
Let's thank the speaker again. And thanks everyone for a great session. Now it's time for lunch.
Try.
Hey, so we're going to do a quick audio check. Speaker, can you try to say something?
Can you say something?
No.
We're testing the audio.
We're just doing a quick audio check, sorry.
Okay. Everybody is ready? So my name is Jung. I'm here this second verification session. We have 3 papers. The first paper will be about the ComSert cast and the ArcMatch, and Yong-Hin Kim will give the talk.
Today I will discuss end-to-end verification supporting integer pointer casting. This work addressed the challenge of verifying both program specification and compiler correctness for programs that use integer pointer casting. Let me start with the motivation. Integer pointer casting is a key feature in C programming, widely used in critical systems like Linux kernel. Our goal is to verify C programs that use integer pointer casting in end-to-end manner from specification all the way down to assembly code. What exactly do we mean by end-to-end verification? As shown in this diagram, we have 3 key components: specification, source code, and assembly code. End-to-end verification consists of 2 major parts. First, compiler verification, which ensures the compiler correctly translates the source code to assembly. Second, program verification, which proves that the source code satisfies its specification. By connecting these 2 verification steps, we can prove that our final assembly code correctly implemented the original specification. Let's explore the key challenge in memory model design, namely the tension between supporting integer pointer casting and enabling compiler optimization. To see this, consider 2 contrasting approaches: the concrete model and the logical model. In concrete model, every memory location has a specific integer addresses. As pros, this makes it highly intuitive for programmers and naturally support integer pointer casting, which is essential for many real-world C programs. However, as cons, the concrete model makes it very difficult to perform sound compiler optimizations. Before proceeding to the logical model, let me illustrate the pros and cons of the concrete model with a simple example. Here's a simple program where compiler performs constant propagation like this. Let me examine this code line by line. Line 1 and 2 declare 2 characters arrays initialized by 0. Line 4 contains the key operations, checking if array A and B are contiguous in memory by comparing address right after array A and the beginning of array B. If contiguous, line 5 writes 1 to A1, which is the same location as B0. Line 6 prints B0, which should be 1 after the previous update. Oh, sorry. However, this conflicts with constant propagation optimization. Most compiler would propagate B0's initial value 0 to the print statement, as they viewed line 5 as modifying array A, not B. Consequently, the compiled code prints 0 instead of 1. This optimization contradicts the concrete model's requirement to print 1. Moving to the other end of the spectrum, we encountered the logical model. where each memory location is assigned a logical address. This approach offers significant advantages for compiler optimization justification. However, its major drawback is that most integer pointer casting patterns become invalid under this model. Let me demonstrate both these benefits and limitations using our previous example. In logical model, A and B are located in separate logical blocks, L1 and L2 at offset 0. When we reach line 4, comparison, we compare pointers from different memory objects, where the pointer L1, 1 is out of bounds. This triggers undefined behavior in the logical model because we branches on comparison between an out-of-bound pointer and a pointer from a different logical block. When the source has undefined behavior, any optimization is valid since undefined behavior means all possible behavior. This enables important optimizations like constant propagation. However, logical model has a crucial limitation. It struggles with integer pointer casting. Consider adding line number 11, where we perform an integer to pointer casting followed by multiplication. The logical model produces an undefined value because logical pointer do not have underlying integer address. This shows why the logical model can't properly handle integer pointer casting patterns. This leads us to our central challenge. Can we create a model that supports both integer pointer casting and compile optimizations? Here's our key contributions. First, we developed the ArcMage memory model that balances concrete and logical models, supporting both integer pointer casting and compile optimization soundly. Second, we built ComCert-Cast, extending ComCert with ArcMage to verify compilation from source to assembly. Third, we create ArcMage logic for verifying high-level specification of program using integer pointer casting. Together, these forms an end-to-end verification framework for C program with integer pointer casting. Now, let's move to the memory model part first. Before presenting our ArcMage model, let's examine its predecessor, the quasi-concrete model from POPL'25. As shown here, quasi-concrete model found a middle ground between concrete and logical models, handling most integer pointer casting patterns while justifying optimizations. However, it could not handle one-pasty and pointer patterns. This limitation motivated our development of the ArcMage model. Let's examine how the quasi-concrete model works and where it fell short using this example. This code is similar to our previous example, with changes highlighted in red, where we convert the pointers A and B into integers IA and IB at line number 4 and 5, and then compare two underlying integer addresses instead of their logical representation at line number 7. Then we convert IA plus 1 back to pointer and compare it with the original pointer A. In quasi-concrete model, we allocate to two logical blocks at line number 1 and 2 like logical model. Line number 4 and 5 cast pointer A and B into integers. Remember, where the model non-deterministically assigned them physical addresses. Let's say OX100 and OX101 in this particular execution. At line 8, here's a key issue. Address OX101 is special. It could be either L1.1 for one past the end pointer of the array A, or L2, 0 for the start of array B. The quasi-concrete model requires that integer cast to pointer must be in bounds, so forcing OX101 to resolve to L2, 0. This creates problem. According to C standard, this comparison between A and A1 should be well defined because they are derived from same block, L1. And they are offsets within one past the end of the block. However, the model sees them as pointers to different blocks, L1 and L2, thereby giving an undefined value. This shows why quasi-concrete model cannot handle one past the end pointer patterns. Let me introduce our ArcMage memory model. Let's see how ArcMage supports the one past the end pointer pattern in this example. First, ArcMage handled memory allocation and pointer to integer casting in the same way as the quasi-concrete model. However, at line number 8, ArcMage takes different approach. When converting an integers to a pointer, it uses lazy valuation, keeping the integer value OX101 until the pointer representation is needed. Now, see how this approach solves the problem. At line number 9, ArcMage compares L1, 0 with OX101 as follows. First, it converts both to pointers via to pointer, and also convert both to integers via to int, and then evaluate both comparisons according to the logical memory model semantics. While 2PTR yields undefined value, 2int succeed with true, then ArcMage selects this defined value true as a final result. Why this is good? At the casting time in line number 8, we cannot know if the programmer means a one past the end pointer or the start of the next object. The intention becomes clear only when the pointer is used, like line number 8. ArcMage's strategies of trying both interpretation captures this reality. Also, this design is sound because we proved that when both strategies given different defined value, they always agree. Additionally, we proved that integer refines pointers in ArcMage. That is, integer representation have more defined value than their pointer representation. This allows safe replacement of pointer representation into integer representation during compilation. Please remember this. Let's move to compiler verification part of our work. We extended ComCert, which uses logical model to support integer pointer casting by applying ArcMage. And let me introduce 3 key challenges in developing ComCert cast. First, we needed to update the compiler while keeping performance overhead minimal. Second, we had to modify ComCert's proof technique, maximizing reuses of its original proof. Third, we added a new layer for assembly without logical pointers, since real hardware's only understanding physical addresses. Now, I will show you how we tackled each challenges. For compiler performance, we developed cast propagation. It's a new optimization to reduce register pressure in register allocation. And we extended value analyzer of original ComCert to track stack pointer casting. for COMSOL's proof structure, we extended memory relation to handle integer addresses. And we extended simulation relations to handle non-determinism and out-of-memory behaviors. For assembly level, we added a layer proving assembly without logical pointers refines assembly with logical pointers. Among the 3 challenges, I will present the first is in more detail. If you can find the details of the others in the paper. In the original COMSOL, pointer to integer casting is treated as equality. This allows efficient register allocation. A single register, in here EBX, handles both variables P and I. However, ArcMage handles pointer to integer casting differently. It's not equality. So register allocation must treat P and I as a different variables and with overlapping lifetimes. So we need 2 registers in this case. This reduces efficiency of register allocation. This is the problem. This is where cast propagation helps. ArcMage guarantees that integer refines pointers, letting us safely replace pointers with their underlying addresses. Using this property, cast propagation replaces P with I. It separates their lifetimes. With separated lifetimes, register allocation can return to using just 1 register. In here, EBX. Now, let me share our implementation result and performance achievement. On the implementation side, our extension to COMSOL added about 24 to original code base to support integer pointer casting. And cast propagation optimization requires approximately 6,600 lines of code. New physical assembly layer needed around 3,000 lines of code. In terms of performance, we achieved 3 key results. First, we maintained full support all COMSOL optimization passes from C-Lite to assembly. COMSOL cast source level language is C-Lite, not COMSOL C. Second, when compiling COMSOL's own benchmark that do not use integer pointer casting, our compiler produced identical assembly code to the original COMSOL. Finally, through cast propagation, we achieved reduced register pressure, which we checked with our custom test program. Let's move to last part. We developed ArcMage logic, extending separation logic to handle integer pointer casting. Most of our operations follow standard separation logic principles. Nothing new here. The key changes is our pointer to integer casting rule. When casting a pointer to an integer, we create this predicate that links the logical and physical addresses under 1 block identifier. This casting relation can freely relate integers and pointers, allowing either type on both sides. This relation provides 2 important properties. First, this relation forms equivalence classes under each block identifier. Second, pointers within these casting relations are freely substitutable. These rules enable sound reasoning about programs using integer pointer casting. Also, we built ArcMage logic on the CCR framework and verified complex structures like XOR list, and now ported both the logic systems and proved to the CRIS framework. In summary, we developed end-to-end verification framework for C program with integer pointer casting through these contributions. Thank you for listening.
All right, thank you. We really only have time for one question. The next speaker, please go to set up.
Thanks, that's an impressive amount of work. I was wondering, with these rules that you have for like lazy integer pointer conversion, it sounds like I could use the same, like I cast an integer to a pointer and I use the pointer multiple times to actually access different allocations, and it would lazily kind of snap to whatever allocation it happens to be at that moment. Is that correct? And if yes, why is that not a problem?
You mean each time I use that integer representation pointer, then
each time you said you determine the logical allocation again, but like I use it once, then I subtract one, I use it again. Now I might use different allocations, which wouldn't be possible under like a PNVIA UDI model.
Maybe we can move this offline.
Okay.
All right.
Okay.
Okay, our next talk is on formalizing graph algorithm with co-induction, given by Austin Kidney. Mike? Hello?
Oh, okay. Sorry.
All right, thanks very much. Hello, my name is Ashin, that's me on the left, and this is the presentation for formalizing graph algorithms with co-induction. This is joint work with my supervisor, Nick, there on the right, and thanks everyone for coming. So this is a paper about graphs. Specifically, it's about functional programming and formalizing with graphs. Split into two halves. The first half of the paper is basically about a functional treatment of graphs. We use a pretty standard representation, but we think we have some new ideas about algebraic and design and co-induction. Second half of the paper is about our formalization in cubical Agda. That's where most of the technical stuff is. I'm not really going to go through that in this talk. This is mainly going to be about the first half. All right. To get started, I want to talk about representing data structures. And I want to make an observation, and that's that functional programmers, like me, really like trees and lists, right? We go crazy for them, right? So things like this, I mean, we have good reason, right? Like a simple data structure like this has a really simple, declarative, and clear data type on the right, and there's no compromise with the data type representation. The abstraction isn't leaky, okay? And also, it's inductive, and we really like inductive stuff because our languages are well suited to it, they support pattern matching well, and this guarantees termination as well because we're using structural induction. So we really like trees and lists. Graphs, on the other hand, don't do so well. So if we look at this kind of graph, the first problem that we'll have is that we have no nice kind of inductive type representation. So we can try with something like this. We're basically representing a graph as a tree where every vertex is paired with its neighbors, so the outward edges. So if you see here, we have the graph, we pick the vertex A, and then we have the two outward edges to B and C. And this looks okay, but our choice of A here is arbitrary. So we could have just as easily picked C as a central vertex. And this is a problem for formalization. So we don't have a canonical representation of graphs. We also have to deal with cycles, which is a problem. So I should emphasize that this can work well for functional programming. Representations like this kind of form the basis of the most comprehensive graph libraries in Haskell. But for formalization especially, the lack of a canonical representation and the presence of cycles are a real significant problem. So our idea was this. What if we just give up on induction and look at the cooler, more mysterious co-induction? And that gives us this kind of a representation. So a graph with vertices of type V is a function from a vertex to its neighbors. So neighbors here is just a type representing weighted sets. So this isn't a new representation. This is pretty standard. But the neighbors type is new, and some of the infrastructure we build up around this is new. So let's look at an example. So we have a graph here that has 3 vertices and 4 edges. And we represent that with this function. So every line in the function tells us the outward edges from a single vertex. So if we look at A, So yeah, if we look at B, we have a single edge of weight 4 to C. Then if we look at C, we have a single edge of weight 1 up to B. So this is an extensional representation. So it's a slightly different style to the other one. We're not listing the constituent parts. We are saying, if you ask me about a vertex, I'll tell you about it. It's a different perspective on things. Another thing that I want to point out is the type of vertices themselves is the same as the vertices of the graph, right? So this graph has 3 vertices because the cardinality of the vert type is 3. And the other thing is that this is co-inductive. So it can actually happily deal with infinitely sized graphs, like this one. So we have IG for infinite graph. And this is a graph where every integer n maps to n plus 1 and n minus 1. Cool. So I want to give just a little bit of detail on the neighbors type. So it represents possibly infinite weighted sets. The weight here is drawn from a monas, which is a monoid that has this kind of partial subtraction operator that you see up there with the dot minus. So 5 dot minus 3 is 2, but then 3 dot minus 5, it truncates and you get 0. And it's also ordered using this thing called the algebraic preorder. The set itself has 2 kind of quotient laws. So it ignores order. So 7b, 2c is the same as 2c, 7b. And when you have duplicate keys, you keep the one that has the lesser weight. So that's the second example there, 7b, 2b, we keep 2b, okay? So to define this type in Agda, we use higher inductive types and quotient types. But if you wanted to do this in Haskell, you could do just the standard trick of defining a new type synonym and promising that you'll be very good and obey all of the quotients and not do anything wrong. And so all of the algebraic stuff that we're going to do on the next few slides totally applies just with this type. In the future, hopefully something like quotient Haskell will be able to make this solution a little bit better. Right, now that we're up to the speed with the basics of the representation, let's talk a little bit about how the algebraic design comes into it. So a big inspiration for this paper was this paper, Algebraic Graphs with Class. And the idea here is to build graphs out of algebraic primitives, in particular the connection monoid and the overlay monoid, or arrow1+. So you can see 2 graphs as an example there. And you see that graph, 1 pointing to 2 and 1 pointing to 3, is built from these kind of atomic parts, 1, 2, and 3, just with the simple operators of arrows and plus. So we really like this algebraic approach. You get all of the advantages of algebraic abstraction, laws, initial objects, and so on. But it didn't seem obvious at first as how we would apply it to our thing. In the Mokov paper, they start with the algebraic stuff and they derive a few representations. We've started from the representation. So the solution comes in the form of arrows. So arrows are a thing, abstraction kind of similar to monads or applicatives, but they're better known for abstracting over pipeline-like things, so parsers or circuits. And the interesting thing here is that the graph type that we've already defined itself actually is an arrow. It's a Kleisli arrow relying on the monad instance for the neighbors thing. But the main point here is that all of the algebraic operators that we're looking for, all the things that we need, can all be actually found in control.arrow, Haskell's arrow library. So let's look at one of those operators now. This is the overlay monoid. It's called that because we basically overlay two graphs with the same vertices on top of each other. So here's its signature. Notice that it takes two graphs with the same vertices. And here's an example of it working. So we have two graphs. Each of them have three vertices. And we're basically placing one on top of the other to get the thing on the right there. So notice that the edge C to B is preserved from the input to the output. And then notice that the edge A to B, when the two edges collide, we take the smaller of the two weights. So this monoid exists pretty much as is in algebraic graphs with class. But also, it's taken directly from the R+ class. So we didn't need to implement anything other than some new type wrappers in order to get this algebraic thing totally for free. And if you want to make it into a monoid, the identity that you adjoin is a graph with no edges. The other monoid that we have is the connection monoid. It's a little more complicated than the overlay monoid. Again, it takes two graphs. But what this one does is it connects the ends of edges of the left graph to the starts of edges of the right one. So if we see an example here. So we see we have two graphs here, each with 4 vertices. And we have one edge in the output. So that edge in the output comes from this edge in the input A to C, and then this other one, C to D. And then using the magic of animation, we can see that it makes this edge in the output. And the weight of that edge is the sum of the weights of the other constituent edges. So this weight is also in the input, but you'll see that there's no corresponding outward edge from B in the other graph, so we have no edge in the output corresponding to that one. So this operator is actually even more fundamental than the overlay one. This is a Kleisli composition. And again, it's taken straight from the R library. The identity in this case is a graph where every vertex points to itself. Cool. So the two monoids that we've seen, overlay and connection, combine to form a semiring. So semirings have been used with graphs for a long time. This is just two example papers that we have here. But also, actually, there are a load of other semirings on the graph type that we've defined that we can just derive again from the R library, right? So like we have this one. Notice that in this one, the type of the vertices changes on the output. So we actually multiply the cardinality of the vertices to get the output on the right. So pretty much all of the operators in the library can be interpreted, in the R library rather, can be interpreted as graph combinators or graph transformations. Okay, now we know how to construct graphs. Let's look at searching through them. So the first thing to notice is that because of our type of graphs, there's a symmetry that we can exploit to get a nice kind of uniform interface, right? So if we look at the type here of depth first search, this is an algorithm that takes a graph, takes a vertex to start the search from, and then returns a list of the vertices in depth first order. So the first thing we're going to do is we're going to generalize this a little bit. And now it's going to return the vertices also tagged with the weight, so the weight of the path it took to get them. Our type of graphs is actually V to neighbors V, or A to neighbors A. So this search thing itself is actually just a graph transformation. So this kind of uniform interface will give us a really nice way to compose combinators to develop search algorithms, which we'll see in a couple slides. Okay, so let's see an example of search on an actual graph. So it's the same graph that we've seen already. And if we call search on it, you'll see that the output is what you would get if you walked through the graph. So this one is in breadth first order, where you start at A, and then you go to C, and then B is the next one, and then B again, but around the other way. So if we look at this entry in the output, that comes from this path along the input. But of course, this search algorithm itself is producing a graph. So the natural question is, what does that graph look like? And it's this. So you see that this edge, this path that we have from A to C and C to B, that corresponds to an edge in the output graph here. Okay. So what we've actually done here is we've defined transitive closure on our graph type. And transitive closure itself can be defined in terms of the semi-ring operators that we had previously as the Kleene star. Okay, so all of this semi-ring language that we have on graphs itself can be used not just to define graphs, not just to build graphs, but also to define search over graphs. So the other example, advantage of our uniform interface is that it makes it easier to build kind of search components that we can combine to make algorithms. So we have, for instance, this one. This is, again, just another graph transformation. And what it does is it attaches to each vertex the path that you took to reach that vertex. So if you had a search algorithm that searched through a graph and then returned individual vertices as a result, just by sticking this path combinator somewhere in that algorithm, now that algorithm return the paths in the result. We also have this one. This filters out edges from a graph according to a predicate. It does that by generating a new graph where there's a zero edge wherever the predicate fails. So we can combine these things to make pretty complex algorithms in this compositional and algebraic way. For instance, here's Dijkstra's algorithm. So it again is just a graph transformation. And what we have is we take in a graph, we say, okay, remember all the paths through this graph. Then also get rid of any paths that have a duplicate vertex in it. And then on top of that, find the transitive closure of that expression. And this gives you the shortest paths through your graph. Cool. So I'm now just going to very quickly run through the formalization that we have. I think this stuff doesn't translate so well to slides or a talk, so this is just going to be a brief overview. So the neighbors type makes up a bulk of the complicated stuff in the formalization because of the combination of quotients and co-induction. When we're doing co-induction, especially in AGDA, a lot of the time we're relying on things like guarding under a data constructor or something like that. And when you mix quotients with that, it can destroy the kind of the uniformity of data representation that you might rely on in order to make co-induction go through the productivity checker. So what we actually do is our neighbors type is defined in terms of semi-group actions. So here it is. It's a dependent pair where the first part of the pair is a function, which is basically a search procedure where you give it a weight and it searches up to that depth that you've supplied. And then the second part is neighborly, which is a coherence condition that says the first part has to actually be equivariant. Yeah. So also in the paper, we have stuff on using the monases that we had earlier to do well-founded recursion. And we also use the theory of completely iterative monads to give kind of justification for termination on recursive equations like the Kleene star that we already saw. And that's my time. Thanks very much.
Okay, we have time for one question. Who's there first?
Quick question. Where's the? Hi.
Go ahead. Answer the question.
Sorry.
Quick question. The definition of a graph is basically identical with the definition of a relation. It just is a relation. That's it. So, what does your work have to say about all the classical work on relational algebra and manipulations of relations?
Yeah, so I mean, it's obviously very related, and there's a lot of overlap between the two. The main kind of technical stuff that we were struggling in the work was with co-induction. So this idea of if you're relying on a co-inductive definition from the get-go, how do you make all of your other proofs go through and so on? So the overlap with relational stuff, you get a lot of interesting things in terms of the algorithms you can define, but the co-inductive stuff that we did in the paper didn't have as much overlap. Does that make sense?
We have time for more questions because there's some technical problem. Please pass the microphone to.
Thanks for the talk. You talked a lot about how to define functions and define graphs, but not so much about reasoning about them. So how difficult is it to prove properties of the algorithms that you define in terms of those combinators, for example?
So it's, it's complicated. The main stuff that we rely on is the semi-ring thing and the semi-ring laws. So we rely on the fact that in our formalization, search is basically identified with the Kleene star, and then we rely on the laws and the algebraic laws that you get as a result of that. And then the completely iterative monad stuff gives us the well-foundedness of each step and that kind of thing. So pretty difficult, but yeah.
Thanks.
Do we have time for one more?
What was the motivation for using this, the edge weights that were drawn from a Monas? Like, that structure didn't seem obvious to me a priori, like when you're dealing with graphs in general.
Yeah, so the reason that you need, we need an order on the thing so that we can talk about shortest path. And then we also need to be able to talk about the difference between two weights, because if we have two paths that are one slightly longer than the other, when you do something like put the other path back into the heap, usually you want to use the difference between the longer path and the shorter one when putting it into the heap, rather than the absolute weight of each one individually. So that's why we need the dot minus operation.
All right. Thank you. Let's thank the speaker again.
This is project.
Okay, our next talk is by Yoon-Sung Kim.
Let me check.
It's going to be about end-to-end verification framework for real-time distributed system. You guys want to change your laptop?
Yeah, I think we need to do that. 했는데 계속 안 돼가지고 시험에 들어서 해야지. 메일로 보내줘야 돼. 일단 메일로.
Try another laptop? Yeah.
All right, sorry, quick delay here as we're figuring out how to use the technology. Yeah, they're doing it now. Took a while to get the slides.
So does it work somehow?
Yeah, sorry for the inconvenience. So let me start my presentation. Hello, everyone. I'm Yoon-Sung Kim from Seoul National University and Yale University. Today, I'm going to introduce my work, VeryRT, which is an end-to-end verification framework for real-time distributed systems. Our research aims to formally verify safety-critical systems like autonomous vehicles, flight control systems, or power plant control systems. These systems are typically designed as real-time and distributed systems for the following reasons. First, they are required to meet real-time constraints for their safety and reliability. For example, an autonomous vehicle must detect and respond to environmental changes before strict deadlines. Also, they require distributed architectures to handle physical constraints, such as placing sensors and actuators in different locations. In our attempt to develop a new verification framework for real-time distributed systems, we have encountered several key challenges. So next, I'm going to introduce those key challenges and our solutions to address them. So let me start by outlining three key challenges. The first one is about modeling timing behavior. So it's about capturing how programs behave over time. The second one is about handling time computation dependencies. Timing and computation are mutually dependent so that they must be verified together, not separately at some point. And the third one is about reasoning about integrated, distributed, and real-time properties. So their combination multiplies system complexity. So we need to manage them in an effective way. So to illustrate the challenges, let's use time division multiplexing as our motivating example. In this system, multiple physical nodes share a single communication channel by dividing time into multiple slots. Let's consider a node that is assigned the grace time slot so that it may send a message only within this slot. And let me walk you through the program code of this node and the expected behavior of this code. We start from the top of the loop, and this circle in the center represents the program state at this moment. First, the program calls gen message, which takes some time to generate a message. Then the node needs to sleep until the time slot begins. And to calculate the amount of time to sleep, it first obtains the current time by a system called getTime. The return value t will be between the call and return times. Then, based on the value of t, a function sleep time computes the amount of time to sleep, which is w, and it is calculated carefully by considering all time jitters and local clock skew. The next line calls the sleep system call, which will return after some time, which is approximately w. Then this makes the program call send within the time slot, and it returns within the time slot. Now, we described the first challenge, modeling timing behavior. In conventional untimed program semantics, an execution tracks only the event order, but not the timing. However, to handle real-time properties, we need to model the timing behavior of programs so that an execution tracks the timing too. And an observable event is paired with its occurrence time. So now the question is, how do we specify the timing in an execution? One naive approach would be like assigning maximum time bounds for each type of instructions and adding random time within the bounds for each transition. But however, this approach will not give a proper estimation on the actual execution time because compiler optimizations significantly change the code structure to reduce execution time. Therefore, we need another approach to model the timing. Then we explain our solution here. Our approach encodes timing assumptions directly in operating program semantics rather than modeling timing from the code. And this lets us use these assumptions during verification. So the timing assumptions now become verification conditions that we validate against assembly code through worst-case execution time analysis or rigorous testing. Let me explain more details with our example. We will start from the time when the getTime system call returns. At this point, the timing assumptions specify the time-bound EST for the user code between the return of the getTime system call and the next call to the sleep system call. So like this, timing assumptions declare time bounds between a call and a return of system calls or a return and a call of system calls so that they are well defined throughout compilation from C to assembly. So based on the time bound, the semantics set a deadline, TD, that is until the next call to sleep. Then the semantics may take some time to complete the user code, sleep time. And as long as the next call to sleep occurs before the deadline, the semantics updates the sleep system call as we did before when we set TD. And to rule out executions that violate the timing assumptions, our operational semantics generates a special event NB, which stands for no behavior, to mark these executions invalid. Then these executions will be discarded when we derive valid behaviors of the program. So in verification, users can leverage the timing assumptions by just assuming that there is no NB in the execution. So now, let's move on to the second challenge. The problem here is that we need to devise a new method for reasoning about timing and computational behavior together, since they are mutually dependent. So to demonstrate this, we will show first how a computational bug may cause timing spec violation, and then how a timing bug may cause computational spec violation. So let's go back to our motivating example. The current figure describes a correct execution where the call and return of the send system call are within the time slot. Now, let's suppose that there is a computational bug in the sleep time function. Then, if the sleep time calculated a value that is too short, then it might send the message before the assigned time slot. So in this case, this execution might still generate correct computational results, but obviously it breaks the timing specification regarding the time slot. Now let's suppose that a timing bug occurs so that the program called send too late. Then the destination node may receive the message at a time that is not intended by the system design. Then this mismatch between the received time tr and the message content m, the node may generate abnormal behavior that violates the computational spec. So to address this challenge, we designed a set of new simulation relations named timed simulation relations. The first one is program local simulation, which is just a standard simulation for matching two program states. This simulation is useful when you want to apply time-independent reasoning to abstract away code-level computational behavior. The second timed simulation is node local simulation. And yeah, this allows reasoning about timing and computational behavior together at the node local level. So at the high level, the simulation works as follows. So in verification, you can assume that identical messages are coming with the identical timing from the network to both source and target node states. Then you need to guarantee that the source node can simulate target node's behavior in terms of the content and timing of each outgoing message. Third, we designed the global simulation that can handle global properties by reasoning about both time and computation. This simulation relation remembers a piece of observable trace, which is useful when we want to eliminate non-determinism regarding execution time. And this will be discussed later in the case study part. So our last challenge is about reasoning about integrated, distributed, and real-time properties of systems. The combination of these two properties multiplies system complexity through their non-determinism. So let's see what sources of non-determinism are present on each side. First, regarding real-time behavior, the execution time of program code and system call are non-deterministic. Also, each physical node in the system has its own local clock with individual skew. And second, regarding distributed architecture, the network communication has non-determinism in message delivery time, drop, and duplication. Also, there are non-deterministic interleaving between the nodes, physical nodes in the system. Therefore, we need a method to manage these complexities effectively. Our solution uses layered abstraction to manage complexity. Instead of handling everything at once, we separate concerns into layers and reason about each layer independently. As this diagram shows, we gradually abstract away the complexities we mentioned in multiple steps. So building on these solutions, we developed VeriRT, a verification framework for real-time distributed systems. And as case studies, we applied this framework to verify two application systems. This is the overall structure of the framework. It supports the end-to-end verification from an abstract global spec down to the assembly level. And the framework adopts layered abstraction, and each layer is facilitated by applying a proper timed simulation relation. So let's start from the bottom layer. For C programs given by the user of the framework, our framework provides formal guarantee that the behavior, the whole system behavior is preserved until the assembly code if it's compiled by ComCert. This is done by proving a lemma in the framework that says the generic simulation relation of COMSERT implies our program local simulation. So we named our extension of COMSERT, COMSERT RT, which runs the whole translation sequence of COMSERT 3.9. In the upper layer, we can abstract away computational behavior of programs against their computational spec. So at this level, the user can apply program local simulation technique to merge multiple steps of the concrete program semantics into one single step in the spec. So we can significantly reduce the number of interleaving as a result. Then we can further abstract away node local properties by applying the node local simulation technique, which reasons about both timing and computation. So in particular, at this level, we can eliminate local clock skew, which is managed by the OS model. And next, the framework provides global simulation to reason about global properties, such as message delivery times of the network. And the user can freely create additional layers for handling more properties, such as execution times. We conducted 2 case studies. The first one is Parseware, which is a middleware program that implements a communication protocol for real-time distributed systems. Second, we verified Christian's algorithm. This is a clock synchronization protocol for distributed systems with a server-client architecture. So in this talk, we will focus on the first case study. Parseware is a middleware that implements the parse protocol. The protocol assumes a physically asynchronous environment, and it provides a logically synchronous view to its application layer. Let's see what an asynchronous system look like. In this figure, there are 3 control units who communicate through the network. And each job is driven by asynchronous message delivery that causes non-determinism in the system behavior. Then let's see what a synchronous system look like. In this figure, the message delivery happens a periodic and deterministic way. So this eliminates non-determinism, which makes the system easy to design and verify. And in this slide, I'm going to show how to deal with the asynchrony in verifying Parseware. So first, let's revisit our global simulation. This simulation relation remembers trace for realigning events. Let's see how we used this to verify synchronization. This is an execution generated by the system model that still maintains non-determinism in execution times. Let's start by matching our initial state with an empty trace. Then, in verification, we can let the target proceed while the spec stays still. And the trace generated by the target is accumulated in the relation. Then, when the target execution has proceeded enough to match the next state of the spec, we choose a step of the spec that can generate the identical trace with the accumulated one. Then we can resolve the accumulated trace, and we can do the same for the next period. So in summary, to handle real-time and distributed behavior, we have addressed 3 challenges, and we use our solution to build the ValueArt framework, which supports end-to-end verification. And on this framework, we verify 2 application systems. So that's it. Thank you for listening.
Thank you. Okay, we will take one question. All right, if there's no question, let's go to the break. Thanks, speaker again.
set of topics. The first talk will be by Shadaj, and he'll be talking about a semantic foundation for progressive stream processing.
Thanks. All right, hi everyone. I'm Shadaj. I'm a PhD student at UC Berkeley, where I work on the Hydra project. And today I'm really excited to share our work on designing a semantic foundation for progressive stream processing. All right, so stream programs are everywhere, used throughout industry for a variety of tasks, ranging from real-time analytics to collaborative editing and even multiplayer games. But the frameworks that we use for writing stream programs vary wildly and have very different semantics that are often incompatible. The most canonical example of a streaming framework is Apache Flink, which uses the traditional model of streams with ordered sequence of elements asynchronously arriving over time. But there are a lot of other systems coming from other research communities that have stream-like semantics but aren't formalized under the same model. Things like Feldera and DBSP from the databases community, which define ways to incrementally process SQL queries over dynamically changing databases. And even things like LVARs, which come more from the reactive programming community, focused on ways to consistently query dynamically changing data. And so our goal with Flow is to design a unifying semantics, which can capture the behavior of all these different types of frameworks under a common roof, while providing sufficient structure that we actually give strong guarantees to the developer about how their streaming programs will behave. All right, so the first question to answer when designing a new streaming semantics is, what are we going to define as streams, and what are we going to be doing with them? So the first kind of step that we took with Flow was to broaden our definition of streams to allow for any underlying data type as a collection, going beyond just ordered sequences. Secondly, we preserved the classic piece of streaming systems in that these collections are going to be asynchronously updated over time. And then we have a variety of things we can do with them. In particular, we're going to take the data flow approach to stream processing, where we're going to take in streams and apply operators that are going to transform them into other streams. And lastly, kind of what makes a streaming program streaming is that we're actually going to be yielding fresh outputs in real time. So when given partial inputs, we want to be yielding partial outputs rather than blocking. All right, so we instantiate this kind of design principles of a unifying data flow language in Flow, which is a data flow style streaming language where you can combine operators that transform streams using sequential and parallel composition elements. The key design principle of Flow, however, is that you bring your own collections and you bring your own operators. So Flow is actually kind of a meta language. We don't provide built-in operators like map or even order sequences, but we provide guidelines and proof obligations for anyone who wants to add these into the language. And so what we're going to focus today is on these elements and the correctness restrictions we have on them. So the first piece of Flow is collection types. As I mentioned, Flow abstracts beyond the traditional definition of just ordered sequences being streams to support many different types. So we support ordered sequences, which are defined by a concatenation operator, which specifies how new data is added to an existing collection. But this concatenation operator can be defined for other data types as well, including sets, singletons, semi-lattices. In the case of singletons, it's kind of a different thing that you might have seen with stream programs before, where you just replace the last value with whatever you're concatenating it with. And this even goes as far as supporting retractions. So this concatenation operator can handle things like removing elements from a set once it's been added. And this is how we use what we use to model things like the incremental SQL engine I described earlier. All right, so now that we've kind of covered the groundwork of how we're going to be structuring our programs in Flow, the main goal of our paper is to define a set of proof obligations and guarantees that we give to the developer about how their program is going to behave. So what makes a stream program good? In Flow, we break it down into two key properties that we think kind of capture the core essence of what developers are looking for when writing stream programs. The first one is a classic property, determinism. We want to make sure that when you feed in the same streaming input, you're going to get the same streaming output. This is fairly straightforward. The second one is a little bit more complicated because it's unique to the streaming domain. As I mentioned before, in streaming programs, we want to make sure that our programs are emitting meaningful partial outputs when given partial inputs. And so we formalize this into a property called streaming progress, which we use to make sure that our programs are actually doing something and not just blocking on input. All right, so let's start with determinism. Now, the most kind of classic way you can think about determinism is at the scope of a single operator, right? If I have an operator like map, again, this is going to be something provided by the user, not something built into the language. We want to make sure that when we provide some input, like 2, 3, 4, the operator may, for example, non-deterministically take elements out of this set in some arbitrary order, but eventually we want to have a deterministic output of the transformation. Now, this might seem good on its own, but as I'm going to show, this is actually insufficient for guaranteeing determinism when you compose operators with each other. To take an example, let's imagine we implemented an operator called fold eager. So fold eager is going to take in whatever partial input it's been received, and every time we re-execute this operator on a growing input collection, we're going to just perform some aggregation. In this case, I'm going to do max. So every time we execute this operator, we're going to take the max of the elements received so far and emit that as a new element of our output collection. So if we imagine some batches of data coming in 1, 2, 3, 4, 5, 6, 7, 8, 9, in an initial execution, we might just execute it after each batch comes out, and we'll emit the values 3 and 6. But what happens if there's some scheduler delay, right? I have many operators in my graph, and my runtime scheduler may choose to non-deterministically pick which operator gets to execute at different points in the program. And so if we have this delay, we actually see non-determinism in the output of the program just because we delayed when we observed the changes to the input. And we want to prevent this type of non-determinism. So that's where eager execution comes in. So eager execution is an extension to the core operator determinism property that we define in our paper. And the idea is to incorporate dynamically changing inputs into the determinism behavior of an operator. So instead of just being deterministic with respect to a static input, operators are required to be deterministic even in the face of dynamically changing inputs. And the way we we prove this is through this kind of commutative diagram where you have two choices. If I have some new data coming in, I could either process the data I already have, then add the new data, and then continue processing. Or I could add the new data first and then process it all. And we want to guarantee that along both of these paths, we get the same result. So as an example of what this kind of forces the developer to do when they're adding new operators in order to satisfy this proof obligation, we can take a look at LVARs. So LVARs is this existing work which shows that if you are performing these types of aggregations, it's useful to aggregate them into a lattice where we have a partial order which requires our aggregation to proceed monotonically. So in this case, what we're going to do is use the max function. And so whenever we add a new element, we're going to guarantee that kind of we take the max of the new element and whatever we had aggregated before. The second piece of LVARs is it requires us to execute only monotone queries over that lattice value. So in this case, we're going to do a threshold query. So we're going to say emit an event whenever this lattice that I'm accumulating becomes larger than 5. And so in one execution where I execute both operators after every batch, I'll emit the event for 5. But you'll see that even if I have scheduler delay, I still get the same output because of the monotone behavior of this query. And so this operator and its implementation on top of a lattice stream type would satisfy eager execution. And again, the kind of point I'd like to drive home is that these proof obligations are local to individual operators. You never have to worry about how it interacts with other operators. You just need to prove it for each operator you want to add to the language. And we guarantee that you'll get determinism in composition. All right, so now let's move on to the second piece of flow, which is streaming progress. And this is more specific to the streaming domain. So let's take a look at an operator like map. This is a classic streaming operator. I'm going to process each elements one by one. And this feels streamy, right? As I have partial inputs, my output is also going to grow because I can just quickly start processing them. But if I take a look at another operator, like fold, this feels fundamentally non-streamy, right? I'm waiting until my stream ends, and then I can emit an element, right? There's no way for me to meaningfully emit some partial output based on this accumulation, where we're blocking on the end of stream. And so especially if the stream is coming asynchronously over the network, I might have this bad behavior where my program might just block indefinitely on this end of stream terminator, which might never show up. Now, if I look at a closely related sibling of fold, scan, Scan is like fold, except as it processes each element one by one, it emits the partial aggregation so far as an output collection. Now this feels streamy again, right? I'm able to emit partial outputs. So we want to formally define a property that allows for operators like scan and map, but disallows operators like fold. And so to define this formally, we actually took inspiration from Flink. So Flink also does not allow operators like fold at the top level over streams. Instead, you have to define these bounded windows to perform aggregations on, things based on time or number of elements. And so we took inspiration from this. So first, in Flow, we introduced the idea of stream termination as an explicit concept. So we introduced this termination symbol, which basically says that all future concatenations to this collection should be ignored. And using stream termination, we actually developed kind of a simple type system that distinguishes from streams that will be guaranteed to bound in finite time and are not guaranteed, may bound. In our paper, we refer to these as bounded and unbounded. And so if we can formally define streaming progress using this type system by taking a look at an operator and looking at its unbounded or may bound inputs. So consider an operator like map. What I want to guarantee is that if I have some partial input, and I let the operator process it all and emit whatever it can, and then I suddenly terminate the input, the output should not change other than also emitting a terminator. Because if it emits something else, that means it was blocking on that terminator to show up. And we don't want the operator to do that. So this provides a very quick check for the streaming behavior. So map trivially satisfy this. If I add a terminator, the output just gains another terminator, and we don't emit anything else. If I fold, for example, this doesn't satisfy streaming progress, because if I add a terminator, well, then I emit a value, which means that I was waiting until this terminator showed up before emitting my partial outputs. But we actually do allow for bounded collections to perform fold, because I have a guarantee in the type system that it's guaranteed to terminate in finite time. And so we allow this when you have a windowed aggregation. All right, so that's all I have time to walk through today. There's a lot more stuff in the paper that I encourage you to take a look at. In particular, I kind of glossed over this proof that if you have eager execution on operators, that guarantees determinism across composition. It's actually a fairly hairy proof, so I encourage you to take a look at that. The other thing is, how do these bounded streams even show up in the first place, right? If everything's coming in over the network, you might think that everything's unbounded. The way we actually introduce these to the language is through a construct for nested graphs. So you can actually take streams and apply operators like windowing to generate streams of streams. And these inner streams will be bounded and can be processed by smaller graphs with iterative processing constructs. So definitely take a look at that. The other thing I'd like to point out, this is a theory paper, but we've actually put it into practice. So as part of the Hydro project, we've been building a framework for correct by construction distributed systems programming. And we're building things like Paxos in terms of this framework. And the core concepts from Flow, eager execution, and streaming progress actually show up as Rust types in this framework. And so I encourage you to take a look at hydro.run, and you can play around with it today. And with that, I'd be happy to take any questions.
So I'm wondering about this stream when you added the empty set at the end, and then you might output an additional element. What happens for, say, a version of the scan function which outputs like n+1 elements, where you want to output the final value in addition to, like, does that count?
Yeah, so currently in the flow semantics, we disallow it. It's meant to be a very kind of quick check that's easy to validate. So we don't allow that type of stuff of like on termination, emit an extra bonus value. Not in the current thing, but we're curious about if there are ways to broaden this property.
Yeah, thanks for the talk. Talking about your operator eagerness criterion, it looks and feels a lot like being a magma homomorphism or something like that, but it seems slightly differently. Can you maybe talk a little bit about the relationship there?
Okay, I'm gonna be completely honest. I think we've not thought too much about the relation. We've had a lot of people come up to us and ask, like the Terminator symbol looks like a left 0. And in fact, our concatenation operator in our paper, we don't require associativity. We don't actually need it for any proofs. It might start looking more like what you're describing if we require those algebraic properties on it, but don't have a very good answer for the relation between those two.
So the stuff around determinism because of scheduling, it does smell a lot about like some commutativity going on. So does the foundation also reason about some commutativity?
Yes, yeah, that's a great question. So the place that, so flow itself does not have any commutativity constraints built into the language. We have ordered sequences. Where commutativity shows up is depending on the definition of my collection. So if my collection is a set, then I might have operators that non-deterministically pick elements in different order, which would require your aggregation, for example, to be commutative. I'd actually point you to Hydro. So in Hydro, we have a distributed setting. For example, if you have many machines sending network messages to a single aggregator, we actually encode in the type system that there's message reordering happening there. And that forces the downstream operators to be commutative in order to satisfy these properties. Yeah.
So asking about the earlier property, determinism, it looked like your formulation of determinism prevents turning in intermediate results like in the max case. Is that desirable? It seems like it's useful to know what's the highest number so far, but then I might get a stream with more intermediate numbers depending on how things are grouped.
Yes, yes, this is a good point. So I kind of glossed over this a little bit here. So in the fold case, I was outputting a ordered sequence, or the fold eager case. That's where determinism broke down. If I were to output a singleton instead, I actually would be fine. I would preserve determinism because you would just be replacing the previous values, and the progression leading up to the latest value would be kind of erased, and that's where you have the non-determinism. So depending on the selection of the type that you're outputting, there are ways to kind of do things like emit those early max results. But observing that might be non-deterministic then, like taking a snapshot of that value. So there are tricks you can play, yeah.
Got it, thank you.
Okay, so next up we have Nobuko. Nobuko will be talking about complexity theoretic questions around multi-party session types.
Thank you very much. And so, Shien and Nobuko at Oxford present the specification and model checking and complexity analysis of session types. And I changed the title because I want to stay my talk as general as possible. And our paper contains the result, which is not specific about multi-party session type, but also very relevant binary session types. I want to focus on these part of today's talk. So you have many of you have benefit from our talk. So first specification we consider is a global type. Global type can be viewed as a message sequence chart or UML diagram. And then first developer write this specification, and then it is projected into each local types, each participant viewpoint, and generate the state machine. Against these state machines, each program is checked independently when they run the program, they satisfy automatically safety, deadlock freedom, and liveness property because you start from the global type. Bottom-up model checking approach is the other way around. First, you have a program, and you infer the local type, which is a set of state machine, and then you apply model checking and check the desired property you want to guarantee. For example, safety, deadlock freedom, liveness. And once it's checked, you can guarantee the property of the set of processes. Now, good point and bad point. So specification, good point is that you can guarantee correctness by construction and protocol conformance because you start from the specifications. Automatically guarantee safety, deadlock freedom, and liveness properties for processes, and also works under asynchronous semantics, infinite FIF or Q semantics. And bad point is that typeability depends on the projection algorithm, endpoint projection algorithm, so that typeability is generally less than bottom-up model checking approach. So what is a good point of model checking approach? No need for global type, great. And sound and complete with respect to the property and larger typeability than top-down approach. And bad point is that need to verify each property of phi. And so probably your local type and set number of participants are many, so that probably it takes time to verify it. And worse, it is undecidable for asynchronous semantics. And so we decided to compare these two approaches objectively, analyzing the complexity of verification in synchronous semantics. Why synchronous semantics is that? Because bottom-up asynchrony is undecidable. And many of the work of the session types are synchronous, even practical like next talk. So we have a top-down approach starting from global type and bottom-up approach. In the bottom-up approach, we infer the types with respect to the subtyping relation. So principal type is the minimum subtyping type. And so first we infer it and check the properties. And interesting things we discover is that top-down approach, first you project it and infer the local type, check the compatibility between the subtyping between projected type and inferred type, has the same complexity and typeability. This is very good because you can calculate total complexity of both approaches. And moreover, you can concentrate to compare the projection subtyping and model checking approach subjective, not subjectively, objectively. Okay? So, to analyze it, we decided to stick existing algorithm and analyze complexity result. But unfortunately, we found out many parts are missing, and we should actually newly invented algorithm and check complete these stories. Not only this, POPL reviewer demanded to ask more and more complexity result filled in during the rebuttal, which makes CN to crazily calculate many other complexity results during the rebuttal. So we have massive result in one paper. And first, top-down, we analyze 4 projection algorithms, both lower bound and upper bound complexity. And 2 of them we are newly constructed algorithms. Second, two subtyping algorithms. One of them, efficient one, we invented by ourselves. type inference. Actually, type inference never studied in the session typing system. So we need to construct the type inference system from scratch. And model checking approach. Actually, we all proved that model checking approach is p-space complete. And we analyze safety, deadlock freedom, and liveness property. And then, according to Shen, and most hardest point of the proof is p-space hardness and liveness, because this is most expensive part. Today, I do not talk model checking part, but I try to introduce interesting notion of type graph. And during our work, we found out type graph is a very useful and different shape of type graph appeared in our paper. I pick up most interesting part. So first thing is you can think about binary session types and internal choice. And there are two internal choice. One is L1 going to 1-1 recursion, and another is going to end. This is just a state machine, but this is a type graph of the local types. Using this idea, you can construct the efficient subtyping checking of the session types. So you can think about tuple of the type T1 and T2, and if T1 move to one step, and T2 simulate, and you can run this kind of simulation game between tuple. And you can think this subtyping checking is very efficient, quadratic because of simulations. However, we calculated existing subtyping inductive algorithm, and in the literature, this is exponential. So type graph is useful to construct the efficient subtyping checking of the session types, and this is valid for the also binary session types. Next, let's infer the types. And to infer the types, first we should note that non-trivial part of the session type is that we have external and internal choice. And first step is a very standard, like lambda calculus. We infer the set of constraints from the untyped process. Second step is very tricky. You build the minimum type graph from the set of constraints. How you can do it? So first, let's think about very simple conditional program. So you have external choice branching to weight L1 and L3 in the truth branch, and L1 and L5 in the false branch. And inside there is an internal choice, try to select different labels. And you can infer the type constraint easily like this, using the standard manner. Now you construct the minimum type graph, and left is a true branch, and there is a this shape, but interesting point is that node is type variable. And if you track this kind of transition relations, and false branch is similar but symmetric. Now you build the minimum type graph, but please note this is neither super graph or subgraph, because contravariant and covariant of the session types. How you can construct the algorithm is that you need to track the set of local, set of type variable. If type variable is superset, actually this is the supergraph, like this. So this is a quite tricky part, interesting part, and we can characterize them like this. And I skip the complexity of the type inference and move to the finally multi-party session types. So we want to compare top-down and bottom-up approach. And we already know the model checking approach is p-space complete. But we have hope of the top-down approach because subtyping is quadratic. And if projection is efficient, top-down is winning. So, next. So this is overview of the properties of the multi-party session type, both model checking and projection algorithm. So first, widest property, useful property, is safety property, which you can guarantee by model checking type soundness. And you can independently analyze deadlock and liveness. And but important part is 3 and 5. And 2 and 4 are useless because 3 and 5 can guarantee the type safety of the session types. Okay? And inside, there are 4 kinds of projection algorithms, strictly smaller than intersection of liveness and safety. But you remember, using the subtyping relation, you can enlarge the property to meet the all liveness property and by some projection algorithm. So now we look at what is a projection algorithm. First, inductive plane merging algorithm is you can now look at the global types. Global type between Alice, Bob, Carol, right? And mu t is a recursion recurse to the beginning. So Alice send Bob and choosing either L1 and L2, and then Bob send the Carol and message like this, because Carol does not know which label is selected. Carol should behave as the same. And that is the first algorithm considered in the original paper. This is quite efficient, actually. And the second one is actually most practically useful projection algorithm implemented in the many tools. So even there is a tail, Carol behaves different. If different levels, you can receive it waiting in the many branches. In this way, you can project this global type using the inductive full merge. Next one is mechanized by David and co-inductive plane merging. And this is actually, you can merge the same branch with the same meaning, even syntactically different. This is actually quadratic. All things are very efficient. However, this expressiveness is probably much larger if you combine co-inductive full merge projections. Now, let's look at what is the complexity. And so, there exists the global type G, where co-inductive full merge projection requires a local type graph size of exponential. How you can construct such spooky global types? So first, you can think about play around the natural number game. Okay? And so P send to R and Q weighted to this recursion, but one of label and A with number L1 is Ni times length, and it recurs immediately. To synchronize it, let's think about prime number, co-prime number, 3, 5, 7, like this. Then if you want to merge these branches, you need to multiply this prime number, but original global type, sum of prime number. So using the prime number theory, this is actually obtained local type is exponential. So in the case of 2, 3, 5, in the global types, you can get this kind of strange local types, exponential. So unfortunately, this powerful projection algorithm, most powerful one, is exponential about projection algorithm. But interesting thing is why you need to write such kind of strange algorithm. You want to write it in practical using the prime number theory. So what we analyze is that actually top-down takes time linear in the size of local type graph of the projection so that most of things are very practical. Not only this, using the recent advance of the projection algorithm by Lee and et al., projection problem I explained is exponential, which means that what size of the local type you can get against the global type is exponential. But projectability problem means that you can judge whether global type is projectable or not. This is called implementability in the some literature. It's actually polynomial type. So that is a very good news. And I have no time to explain how we analyze the bottom-up model checking complexity, but I stop it, and what we can say is that we need to encode some problem using the very big state machine. And this is quite a lot of work, but I will conclude my talk. So top-down and writing specification or stream diagram and so on is generally very powerful and more efficient in the many realistic cases. And bottom-up model checking complexity we analyzed is that exponential of the size of the local type graph. So many cases it's going to exponential model checking approach. But top-down specification approach is most of things are polynomial, even co-inductive full match, which is a very powerful one. It's most of cases is polynomial, and implementability is polynomial. And apart from this, I introduce notion of type graph. If you want to construct your own type inference system, probably this type graph notion is useful for session type system. Okay. Thank you very much.
Thank you for great talk. So I think in this talk you consider linear time, liveness, and safety properties as other model checking properties. So I'm just curious about do you think you can extend it to the more other temporal logic like CTL and or hyperproperty logic?
This I don't know, but actually our case with model checking is really P-space complete for this particular safety, liveness, deadlock freedom, safe properties which you can guarantee by projection algorithm. Different property probably much more quicker, and these things it depends on the property, but it is likely exponential.
Yeah. I see. Thanks.
Nubugo.
Yes.
Just one quick question. You said that this works for synchronous, right?
Yes.
So what happens in the top-down setting if you have asynchronous semantics?
Okay, can I use my slide? Sorry. So asynchronous case, actually, we have a similar kind of Venn diagram. And actually, there is a group of studying to asynchronous both top-down and bottom-up. And top-down case, this asynchronous subtyping can enlarge to the liveness property. This is actually going to both undecidable, model checking and subtyping, going to undecidable. And several work of the asynchronous subtyping, decidable subtyping is studied in the literature's binary case, and which enlarged to this typability up to here. Another one which is studied in the projection of the asynchrony studied by Lee and et al. Is that you can directly, this is better. You can directly get this subtyping using subtyping relation and projection. And the comparison between these two approaches, and starting from synchronous projection and asynchronous projection applying subtyping, is not compared yet. So this is a kind of future work.
Okay, next up we have Yu Yao, where he will be talking about how to combine timing constraints in message passing protocols and semantic foundations for this.
Sorry.
Thank you for the introduction. So I'm here to talk to you about semantic logic relations for timed message passing protocols. So this is joint work between Carnegie Mellon University and the good guys at the University at Buffalo. So I want to start by setting the scene. So this talk is about time. Time is an important element in computing. What do I mean by that? Well, computations takes time, and computations also need to be on time. The first notion of time is captured in the notion of cost. It is the intentional property of the program. But that's not why we are here. We are about the second one. This work is about specifying, programming, and verifying timeliness of computations using type theoretic methods. So what do I mean by timeliness? I would like to introduce that with examples. So this is a protocol description that I take out from the documents, which says your SMTP server, which is your email server, ought to have a set timeout of at least 5 minutes awaiting a command. So this specifies the condition where the command, timing condition, where a command or a message ought to be arrived. And there are actually more examples of this kind of specifications. And if you squint really hard, you will notice pattern. So every one of the examples have a verb, an action that talks about some sort of communication. And there's a condition which talks about when this communication ought to happen. So this suggests that we should think about a process calculus where communication is a primitive that is enriched with capabilities of copying about timing constraints. But that's actually not it. The systems we were talking about here are almost always heterogeneous. Now, what do I mean? I say heterogeneous in the sense that the system is made up of components that are not written in the same language. Sometimes you don't even have the code for the language, but you do still want to be able to provide whole system guarantees about the timeliness. So whatever we do, we have to account for that. Toward these ends, this work contributes a process calculus and an operational model that allow you to capture the execution of timed message passing programs. So you have messages goes around and happening at specific times. And we also distill a specific specification language for these timed protocols. And we are in the form of session types. We're enriching session types to allow them to specify timing constraints on top of their capability of specifying communications. And we tie these two things together using logical relations. And we strongly believe that the logical relations development is the heart of this development, because we strongly believe the logical relation development is the heart of this work because through semantic typing, we are tying together this automatic verification through type checking in composition with some manually verified components and provide you a whole system guarantee. So to get things started, I want to start with a crash course on intuitionist linear logic session types. So these are process calculus. So in these systems, here we have two processes. There is a sensor and there's a controller. The controller is like Google Nest, like think your home system controller. And these are the two processes in our system, and you connect them with a channel. The channel is a bidirectional channel in a sense that the message can go both ways. And the types in these kind of systems, types specify the protocol on the channel. Who ought to talk to who, then what's next. The intuitionist nature of the system gets exposed in the way that the channel differentiates a provider and a client. And in the intuitionist setting, when you specify protocols, you're specifying exclusively from the perspective of the provider. So if you say send, you mean the provider send. If you say receive, you mean the provider receive. So that's the intuitionistness of the system. And what kind of protocols are we talking about exactly? So here is a protocol diagram. So these states are called protocol states. And the edges on the arrow talks about what operation or message ought to happen to move to the next protocol states. Question marks means receive. They're called queries. And bands are called shrieks or sends. And the letters means labels, and the V underscore something, these are values, functional values. So this describes the protocol of the sensor, and there are basically two branches. And first, it asks you to make a feature selection. So you can either ask for only the temperature data, or you can ask for the temperature data along with a air quality data. So our goal here is to associate each protocol state with a type by building it up gradually. And we want a type that specifies for the entire thing, which means we want a type for the initial state as 0. So the first step of, so here the green ones are basically the state that we are currently in, and the yellow ones are next states. So the first, we say A0 is ampersand A1, A2. It means that A0 is a choice for the outside world to pick between two possible choices of features. On the left-hand side, you have S1. That means we are taking only the temperature data. So let's go with that path. So on S1, the protocol says, the sensor will send you the measurement data, then continue with S3. That's what this band tau temps means. Now we are on S3. S3 just means, I'm going to send a closing signal, and that's the end of protocol. So that's it. And we do the same specification, do the same dance for the second branch, where the protocol says, I'm going to first send you the temperature data, then I'm going to send you the air quality data, then I'm going to close consecutively. Now we put the times in. So due to the construction, the sensor requires 30 milliseconds to warm up before taking the temperature, before taking the air quality data, and requires 20 milliseconds to cool down. So how do we accommodate this in our types? Well, the way we do this is we annotate each type connected with T.P, basically a condition, which says this communication can only happen at the time T that satisfies the predicate or the condition of the proposition P. And so here we are saying that T3 is greater than T2 plus 20. T2 is the last time that anything is communicated. So it says, well, the next communication need to have at least 30 millisecond spacing. And here, similarly, T4 is greater than T3. Plus 20, meaning, you need to wait at least another 20 milliseconds after the last communication. What you notice here is the binding structure. We are not, the binding structure allows you not only specify the constraint, but also bind the time of communication. So the next time you can use that to specify what ought to happen the next time. We do have a type system, but we don't have type. I think the core of the talk is logical relation. So let us go into semantics directly. So we set up the semantic system using operational semantics. And the key idea here is you want to think about the execution of the system as a sequence of instantaneous communication steps happening at increasing time. So you have these like each of these instantaneous time, each of these steps happen like T1, T1 prime, T2 prime, T2. These are all instantaneous, but the time they happen are increasing. And we formally capture this by using two components. One, there is a timed multi-step reduction judgment, which says, you start with this time, this configuration, end up with that time, that configuration. And the way that we handle these instantaneous time is using a timed label transition system, where the upper part of the alpha is the action of the step, and the lower half T means at what time the transition happened. So this is a pretty box standard label transition system, except the key rule, the communication or synchronization rule, says to synchronize, both sides need to synchronize at the same time. This is important because in our system, if you're a provider, you are allowed to specify a time that you want your communication to happen, and we are only allowed the transition if the time that the transition happens satisfies the condition. That's what's on the bar. And if you're a client, you get to pick what time that you want to happen, and the transition is guaranteed to happen only at the exact time you pick. So there is no wiggle room in the dynamics. Now, because the desynchronization rule forces them to happen at the same time, there is no ambiguity in terms of which transition happens. At what time the transition happens, it is guaranteed that it satisfies both the condition set and satisfies the wants of the client. We're now moving to the logic relations. The goal of the logic relation, as we said, is to support verification for encode. So the key insight here is a notion of semantic or behavioral typing, where types are really classifiers of program behaviors, and in our case, classifies both the temporal and the communication behavioral processes. In these proofs, you have fundamental lemma, which basically turns a syntactic well-typedness judgment into a semantic entailment, which says, as long as you're giving me components that we know are semantically well-behaving, you can compose them with other components and get a whole system guarantee. So this is important, exactly because the assumptions can be established in any way possible, using model checking, using multi-party session type, using any method that you want. As long as you can show it satisfies the semantic requirement, you can put it together with another piece of code that you're either written in our language or not, and you get a whole system guarantee that is very strong. Now, our logic relations consists of 4 main definitions. This is a lot. Usually one logic relation is enough. Now we have 4. But don't worry, we will break these down into pairs. So the first pair is the left half and the right half. So we call these things latent versus urgent interpretations, denoted by the letters L and V. So these are like these expression and value interpretations. So the urgent interpretation says the configuration must be able to do the communication right now without any passage of time. And the latent interpretation says that the configuration is capable of doing something in the future with allowing the passage of time. Now, to account for the passage of time, the latent interpretation requires you to externally submit these called computable trajectories, which describes how the transition transitions through time as a witness. And it is exactly the treatment of the witness that enables the second dualizing pair, which is the upper and lower half. And we will talk about how this works later. But the important thing here, we have these star interpretation, and we have these like non-star interpretation. And the star ones can be think about the interpretation being seen as needed, and the green ones are stronger. These are like as guaranteed. We'll get into that later. I would like to start with the urgent interpretation first because it's more straightforward. So here it says the configuration omega ought to behave according A1 external choice A2. This external choice behaves very much semantically like a conjunction at a Cartesian product. So it says a configuration omega is right now acting as this type if it can receive a label left and reach some omega 1, and we know omega 1 is behaving according to A1, and so that's the conjunction part. That it can receive labels right and reach some omega 2, and omega 2 is behaving according to the second component. So this is very much behaves like a Cartesian product, and the labels can be thought of like sending them with the projections that you want to take. Now with that said, now we can move on to talking about the latent interpretations. So these, as I alluded to, the star ones basically says omega is good as demanded from the perspective of one particular client, and the non-star ones are giving a much stronger guarantee that's saying it's good just as guaranteed straight up, and will be set up in the way that the non-star one actually implies the star one. I think it's actually better to understand these in terms of the proof obligations they ought to satisfy. So these star interpretations, we call them future proof, because it says if you have a promise today, the promise still stands tomorrow. If you know something that is good today, you move time forward, you don't suddenly lose the guarantee. It's still good even if you move time forward. So in that sense, a guarantee as established is future proof. Now, dually, these provider guarantees, these non-star versions, requires a much stronger version that is dually past proof. What it means is if you know something's good at t prime, and you know you can get to t prime from t by doing some computation, then you can backwards extend the guarantees to a past that is t. So the star ones allow to move forward, and the non-star ones allow to move backwards. And if you know the logic relations, the non-star version basically only requires forward closures, and then the star versions here essentially is doing a time generalized version of the backwards closure. So you are closing backwards, but you're closing not only just transitions, but also time. And this shows up in their formal definition as this adjunction-like structure, where in one case, in the star version, you say, oh, I only need to guarantee any time that is in the future, I need to be good. But the other side, you are saying, oh, anything I'm quantified over, I'm not bluffing. I'm saying I'm only quantifying I'm only talking about things that can actually be reached. Everything I talk about is in the future. So I think this is a very constructive view where any claim that you make has to have like computational evidence to back it up. You cannot make an argument to say, oh, I will do this yesterday just because your client cannot get to yesterday. So our work is, I think, I want to talk about related work. Our work is understood in this general context for 3. You have these session types, and the one that's most related is the intuition linear logic session types. You have other methods using multi-party session types and using time automaton to do verification with time systems. And our use of logical relation reminds us their use in the Iris framework, in Rust Belt, and more recently DIMSum, which also uses a label transition system to support foreign code and stuff, and also reminds us of semantic typing. So in conclusion, we propose a process calculus and type system for writing and verifying programs with timing constraints. We validated the semantics with logical relations. Our system supports compositional reasoning of timeliness, automatic verification through type checking, and you can put these things together using logical relation to verify opaque components and have a full system guarantee. There's a concrete example that's in paper that I welcome everyone to check out. Our future work wants to incorporate costs, like the intentional aspect of time, into our framework. So you're allowed to say that, oh, I will make this deadline even considering that I'm going to spend this time computing the output. And we also want to support periodicity, that something happens over and over again in time through the use of recursion. What else in the paper? We have a type system actually set up that matches very closely with the semantics. You can see how we basically go from semantics and we internalize all these semantic properties into syntax using a type system. And we have these like compatibility judgments allows you to move a type between the stronger star guarantee to non-star guarantee and back and forth. And we also have actually pretty algebraic treatment of how we manipulate computable trajectories. These are the biggest part in our proof. These algebraic operations contribute a lot. And finally, we actually have a DSL implemented in Rust. We have a lot of timing constraints to discharge, and we discharge them with SMT. This works pretty surprisingly well, I will say. And we have, like I said, the full-fledged sensor example in the paper. Thank you.
So I'm actually curious, and perhaps I missed it, but do you consider real time or discrete time, like all these semantic relations?
Oh, so the way that we set up the logic on time is actually pretty free, is basically whatever you like.
Mm-hmm.
You just need to have some basic assumptions, like for example, you validate transitivity and stuff. Our system right now only checks the discrete time, and then actually it needs to be natural number index time. It's not even full integers, but it is possible to extend to a real-time situation, but you would lose probably, like for example, a lot of the benefits you get from the SMT solver.
Right. Okay. Thank you.
Sorry. So you treat the unary logic means that you are not doing binary logic, which means that you are not investigate semantics equivalence or time to semantics equivalent, right?
That is a very good point. We do have plans in the future to extend it to a binary situation to capture like equational reasoning and stuff. I think the unary one is a good start, and there is already a lot of like constructions. For example, we need to figure out how to algebraically treat like trajectory and stuff. So I think this is a good first step.
I had a question about the next slide, I think. Yeah, so here, the definition of V on this and, I was expecting it to have V on these parts, but it's using L instead. Is this a typo, or is there something interesting going on here?
There is. So generally, when you set up this like expression versus value, once you the values only guarantee their topmost outermost behavior, and once you get through that, you peel that off. Then what you're exposed is something that may be capable of running again. That's what this is exposing. we can probably set this up like more explicitly in a type structure where we differentiate, like we use like something like a fine-grained call by value calculus to make this more explicit. But we think this adds to complexity, but not really make the problem clear.
But wouldn't this mean then that like it doesn't have a unit, for instance? Like if you had A1 and false or something, then that wouldn't be equivalent to A1 because A1 and false would introduce this additional stepping action.
Oh, okay. So what happens is at the L interpretation, like the latent interpretations for the unit types are, I need to be very careful with this, but very close to being an actual unit, but not quite. I think this will be much clearer if we actually separate out the semantic domains more explicitly. But here's what we did.
Okay, so rest of the questions can be delegated after the last talk.
Yes.
But I don't know. Okay.
Okay, so next up we have Dhruv. Dhruv will be talking about verification of DNS.
Yeah, so the topic of my talk is reachability analysis of the domain name system. My name is Dhruv, and I'm the information security group at ETH Zurich under the supervision of David Basin. We don't really see this name very often, where you kind of merge reachability analysis and domain name system together. So today we'll be like looking into what the problem really means, and hopefully you won't be needing coffee by the end of until the end of the talk. So the structure of the talk, in this talk, I'll be first giving you a slight overview of DNS because, in this talk, I'll be giving you a slight overview of DNS because I realize that many people don't really know the nitty-gritty details. Next, I'll be talking about the problem, then the state of the art, and finally, the results, and then I'll conclude. Okay, so what is DNS? And we start with a gig. So let's say you're at a party and you're getting drunk, and at some point you really want to go home. So you call a cab. And you tell the cab driver you just want to go home. You don't tell him where the home is. So the scene one is the cab driver is a creep. He already knows where you live. And he just says, well, come on in, I can take you home. The more normal scenario is the cab driver gets confused and just asks, OK, where is your house? I don't know. And at this point, if you really want to go home, you will tell him the real address, which would typically comprise of a street number, a city name, a country code, postal code, or something, like something a bit more concrete than just home. And this is pretty much what happens within computers as well in the internet when there is an Alice who wants to, let's say, visit a certain domain. What she does is she asks her browser that she wants to go to inter.net, for example. And the browser then forwards this query to something called a resolver, which is typically your internet service provider. And if the service provider already knows the answer, which is the IP address of the computer that you want to reach, or the server that you want to reach, okay, sorry. Now that should not be dropping. Okay, so if the resolver does not know the IP address, it then forwards this query to a name server, which is lying somewhere out there in the internet. And the name server also has an IP address of its own. The query typically contains two portions. One is a domain name, which is basically the query that was the domain name that was initially queried, and a type, in this case, that's A, which is asking for the IP address of inter.net. The name server then checks its local information and gives back a response, which is typically a bunch of resource records. And a resource record basically is a tuple which contains 4 parts. The first part is, again, a domain name. The second part is the type of the resource record. In this case, it matches the query type, but it may not always do so. The next part is something called the time to live, which kind of tells the resolver how long he or she can reuse the same record, like this piece of data. And finally, you have a value. In this case, the value is an IP address because the type was an A type. And there are a couple other types. We won't be going into a lot of types, just going to cruise. OK, so but in the network, we don't have one name server. We have multiple name servers. And typically, the name servers are arranged in a hierarchical pattern, where the top name server is called the root. And below them, we have various domains and subdomains. And there's a tree-like structure. And once again, we have Alice, who's asking her resolver to go to inter.net. And resolver typically, like, there might be a question, which is, how do you know whom to ask first? And this is where the resolver is usually hard-coded by at least one name server in the network, and that name server is usually the root of the network. So the resolver then forwards this query to the root name server. The root name server's response, well, OK, I don't know where inter.net is, but I do know someone whose name kind of matches the query that you just sent, which is a .NET name server. Why don't you ask him? And to do that, it gives back a response which contains two records. The first one is a delegation, which is the red arrow, and the NS record. It says that going forward, every time you see a .NET query, just go and ask .NET, don't ask me. And .NET lives in the IP address IP3. OK, so the resolver then forwards this query to IP address 3. Once again, the .NET name server says, well, I don't know where your query is, but I do know someone whose name matches even more with your query. Why don't you ask him? And the resolver goes forward and asks the same query to ns.inter.net, which is at IP address 4. And at this point, the guy says, OK, I do know where you want to go, and this is the IP address. Have fun. But some things can go wrong. So what if, after all of this, the final name server ns.inter.net is actually malicious? And instead of giving back an IP address, it says, well, I don't know where inter.net is, but I do know someone else whom you can ask. However, and not just one person, I know like multiple people whom you can ask. However, at that point, he does not give the IP addresses of these people. So now the resolver is stuck figuring out where to ask next. It knows the names of these servers, but it doesn't know where they live. So it must first resolve, and that's DNS protocol, these name servers' names first. And to do that, it again goes back to the root. The root now says, well, you need to go to the .com name server. And at that point, when it asks the .com name server, .com clearly knows that ns1.inter.com is nowhere in the internet. So it just says, I don't know, and doesn't exist. So the resolver says, OK, fine, no problem. Why don't you give me the IP address of the next guy I received? Well, again, I don't know. And finally, why don't you give me another one? And at this point, the name server is clearly confused, and it's just its traffic flow is just bogged down by these bogus queries that are being asked by the resolver. Both are busy. And this is something called the NXNS attack, which was revealed in 2020, and it's mildly severe. And that were found in all the resolver implementations out there. So this is how things can go wrong, and this is something that we would like to catch before things are deployed. OK. So this attack kind of belongs to a class of attacks called DOS attacks, which stands for denial of service. And that's because the name server can't actually respond to real queries and is getting stuck doing boring stuff. And it can be seen that in 2022, DNS was 20% responsible for the class of all DOS attacks, and recently increased by a lot. And in 2024, it was actually responsible for more than 50% of the DOS attacks on the internet. So clearly, we need to do a security analysis. And because the scale of this whole thing is huge, we want to do it in an automatic way. So that's it with the motivation. And now let's do some math. So we have the network. What does the network really know? So network is basically just a bunch of name servers which have IP addresses. And each IP address or server stores some local information, which are just bunches of records. So you can actually represent it as a function which just takes IP addresses to bunches of records. Okay, and we call this a zone file configuration, this function. And typically, a zone file configuration uniquely determines the behavior of DNS because that's just all the knowledge the network has. Okay? So what is the problem? The problem that we are interested in is asking that given a zone file configuration, which is this function, is it possible to have a DNS attack, and this attack being specified by a trace property phi? And typically, we actually represent the trace property phi by an automaton that represents the trace property, the class of languages, the class of traces which are bad. And if there's an attack, you would also like to report the attack. Okay. So there has been a lot of work since long, long back. And until 2020, the main way of working on this was testing. And I'll be comparing a few more works across 3 main metrics. The first one is soundness, which basically means that if I report an attack, it is an actual attack. The second one is completeness, which means that you're actually exhausting the set of all possible behaviors. So if in the absence of attacks, you're also reporting that. And finally, we have robustness, which means that if ever the DNS standard changes, how easy is it for you to change your internal model to kind of keep yourself up to date? So in testing, we have soundness because you're basically just simulating the real world model. We don't have completeness inherently. And we have robustness because, once again, you're just simulating the real world model. So since 2020, there have been 2 works, particularly groot and DNS mod. DNS mod is basically a mod wrapper, like a symbolic fuzzing wrapper around groot. And both of these have tried to give a formal treatment to DOS analysis. However, groot lacks soundness, completeness, and robustness. At the time of publication, groot was actually considering a very limited model of DNS, and it was sound with respect to that, but it was still not complete, and it was still not robust. DNS mod, on the other hand, is robust because at the base, it's just using rewrite rules to kind of change the semantics of DNS, but it also lacks soundness and completeness. So what's the goal here? Clearly, testing cannot ever get completeness. So what we would like to do is at least get soundness, completeness, and robustness using formal treatments. And this is also what are the contributions of this work. OK, so how do we do it? Let's consider the model. The name servers that we talked about are fairly simple. They basically just get a query and give a response. And they just look at the local databases. They never gain any knowledge, lose any knowledge, so it's stateless. Resolvers, on the other hand, are complicated characters. They keep 3 main components in their state. The first thing that is keep is a priority list of name server domains to query. Now, it's important to note that they store domains and not IP addresses. So they store the names of people they can ask. Next, they store a cache of records. Oh, sorry, that's a mistake. They store a cache of records, and each record has its own lifetime, which is the time to live that we just saw. After that, the resolver cannot use these records again, and these are received from responses. Finally, we have a stack of pending queries, and this can occur in the attack that we just saw. For instance, if you're asking, if you want to go to sickplan.org, and there is no IP address that you received, and instead you get a delegation to ns.sickplan.org, you will now be pushing this onto your stack and querying that first, stowing away your initial query. So now what's a poor man's approach for this thing? You have these 3 components, and for the first thing, you will store it as an ordered set of domain names. For the cache of records, you can just have a bunch of timers, with each timer identified by a record element. And once the timer is out, you cannot use a record anymore. And you have a stack of pending queries, which can just be represented by a stack of queries. OK, so this means that you finally have a message passing system where name servers are just finite state systems, and resolvers are push down systems with timers. Now, while this may seem easy, there's a catch. And the catch is that all of these things, all these components that we just saw, have domain names stored within them. And the number of domain names we have are huge. And sometimes you even need to store sets of domain names, and that makes your configuration space exceed the number of atoms in the universe, just to put matters in perspective. OK, so as good formal methods people, what we do is we abstract. And in this paper, what we define this as is a syntactic domain congruence, which depends only on the zone file configuration and not on the behavior of DNS, so to speak. So we represent DNS by a free monoid over the set of all strings using an underlying alphabet. It's not important what the alphabet is. And what we do is we abstract it and we bring it down to a finite monoid. And this is typical in algebraic language theory. The way we construct this homomorphism is by parsing the zone file configuration, the records in them, and carefully constructing some regular languages, and then using their syntactic congruences, which is very close to Myhill-Nerode congruence, as building blocks for the finite monoid. And what we have in the end is that if 2 domain names are mapped to the same element in the finite monoid, they are coined to be equivalent. And we have some couple of cool properties, whatever these may mean, and we don't have enough time to actually go into that. But essentially, it conveys that if D and D prime are equivalent, they're semantically identical for DNS. That means DNS cannot distinguish between these 2 domain names. So once we have this function with this homomorphism, we again take the inputs that we have. We lift these inputs in the abstract world to the abstract world, and we have zone file configurations and automata with finite monoids as the domain names. We then use the poor man's construction once again, but this time we have finitely many domain names. And this finiteness is actually much smaller than the initial finiteness we were talking about. And what's more is that any trace in the abstract model is having an equivalent trace in the concrete world. So you can actually map back. And this is proof using a generalized notion of bisimulation that we also proved in the paper. But note that at this point we have a message passing system where potentially it's possible for multiple components to cyclically talk to each other. And this is something which is Turing complete. And hence, if you're talking about reachability analysis of such systems, it becomes undecidable. So this is where we made another observation where we showed that DNS is in fact eager, which means that in certain portions where actually packets are transmitting, as soon as I send a packet, everything else stops, and the person is literally waiting for my message to be received, and I'm also waiting to receive a response. Until then, I'm not going to do anything. And this is something called as eagerness, which was introduced in 2010 by Heusner et al. And using this, it actually becomes possible to reduce this model to a simple pushdown system, which is trace equivalent. That means any trace here is actually also a trace in the previous model. And now we have a finite automaton, we have a pushdown system, and what we do is we just ask the language emptiness problem for this model. And if the language is non-empty, you can actually get a trace, and if it's not, that means the situation is safe. If it's empty, then the situation is safe. Okay. However, the complexity of this algorithm is pretty bad. It's doubly exponential in the size of the zone file configuration, which means that if you have a huge zone file configuration with like, I don't know, 100,000 records, then yeah, it'll take time. Okay, so with that, I would like to summarize that we have come up with a sound abstraction, which is facilitating a decision procedure for DNS verification. Then it adheres to a generalized notion of bisimulation, which allows concrete witness generation. And at the time of submission, we didn't have an implementation, and the reviewers gave us a lot of heat for this, but we now do have an implementation, and it's currently ongoing work in progress. For future work, we would like to extend this setting to multiple ISPs, because that's what's happening in the network. However, it's not really needed for actually recovering most of the common attacks. And we would also like to dynamically update this distributed database, because that's also something that happens on the internet often, like when you want to update something in the local databases of name servers. So with that, I will be opening the stage for questions.
Thanks. Perhaps two short questions. One, does it make sense to consider any temporal properties besides plain reachability? And the second, any lower bounds, proved lower bounds?
Okay. So about temporal properties, there's something which could be a resource consumption feature. And this is related to some of the attacks. However, at the end of the day, the temporal properties would just boil down to symbolic properties, and they can again be represented by some sort of finite state machine, which kind of follows through the typical emptiness of timed automata. So, okay, there is something for liveness which is called availability. The thing is, this is kind of like a one-shot verification. So once you check your zone file configuration, you don't need to check it again. You just deploy it on the internet, and everything works. So availability kind of makes sure that all the servers in the network are reachable. And that's something that is equivalent to liveness when we talk about in the world of the internet, let's say. However, sometimes if there are dynamic updates, then liveness becomes a thing, because with an update, now suddenly something may become unavailable. And yeah, these will be questions that we can ask there. And yeah, that's something that I'm also thinking about, but I don't really have an answer to yet. And about lower bounds, there was a paper which actually showed that DNS is at least as powerful as a pushdown system, which kind of is something that we already showed. But well, it's just kind of like saying that you have a resolver in the network or not. And that makes the complexity at least cubic. But there's nothing better that is known yet, and it's something that we have also not looked into. We just looked into an upper bound.
Questions? Okay, so then let's thank the speaker.
It's time to start the last session of the conference, of the main conference at least. So it's about speculative execution, which is not always good. And the first talk is by Xavi on do you even lift strengthening compiler security guarantees against spectre attacks? That would like less of those, so let's see how it goes.
Yeah, thank you for the introduction. My name is Xaver Fabian, and this is joint work with my collaborators Marco Guarneri, Marco Padrignani, and Michael Backes. So first, let's talk a little bit about what the Spectre attack is. Spectre attacks exploit speculative execution to leak confidential information. And speculative execution is a feature of modern processors to speed up the execution time of programs. Generally, it predicts the outcome of certain decisions, like for example branches, and speculatively executes code. If the prediction is correct, we gain a speed up and everything is good. But if the prediction was wrong, we need to roll back the architectural state of the program. However, the microarchitectural state, which includes the buffers that the processor uses, are not rolled back. Thus, there's an actual footprint of the speculative execution which the attacker can observe in the caches. Let us look at a small example. Here we have this little code snippet where we have a bounce check on this array A for a specific index. Now suppose your index is bigger than the size of the array A, and your processor now mispredicts the branch and still continues executions in line 2 and 3. Line 2, we have an out-of-bounds access, which can contain secret information, which is then stored in this Y variable. And in line 3, we leak this variable inside the cache of the processor via the access into the array B. Thus, this line 3 is a footprint the attacker can observe from the speculative execution and thus gains secret information. So in general, Spectre circumvents many well-established secure programming paradigms. And different versions target different facets of speculative execution or different predictors. For example, there's prediction on conditional jumps, indirect jump predictions, return predictions, and etc. And there are new attacks found to this day. Now, of course, people developed countermeasures targeting the different variants, which are implemented as compiler countermeasures or compiler passes, and also implemented in mainstream compilers. Here we use the square brackets to indicate a compiler for the symbol, and the superscript is used to indicate which countermeasure we are looking at. And the subscript is used to indicate which specific Spectre version is targeted by this countermeasure. Furthermore, we use this little goes with this subscript, again like this SLS or J, to indicate the semantics for this kind of speculative execution. Okay, now let us put everything together what we already have. So in the bottom row, we have like the semantics of a processor which only has the non-speculative execution. And in the row above, we have the different kinds of hardware with specific speculative execution enabled, leading to the different kinds of Spectre attacks. We can also see that those compiler countermeasures are at this level as well, each targeting a specific variant of Spectre. So are we done? Well, the amount of white space I have on the slide indicates not. So what's the problem? Well, the processor uses all these prediction mechanisms actually at the same time. It does not use only branch prediction or indirect jump prediction. It uses both of them. So it uses a combination of those prediction mechanisms. Thus, our picture looks more like this. We get this lattice of the different kinds of combinations or different facets of speculative execution. And there are lots of combinations. And our problem right now is that our compilers are at this bottom row, and their guarantees are at the bottom row. So this leads us to our main question. How can we lift the security guarantees of those compilers to those stronger attackers higher in the lattice? Now, before we can really talk about this lifting process, we need to look at the interactions of the two source semantics x and y when combined, or combined semantics x plus y. And here we use traces to capture the observations the attacker can make during the execution of the program. This includes load and store observations, but also the program counter. Furthermore, we are interested in leaks that happen during speculative execution. So we add this little start observation here with a subscript X to declare that this speculative execution or speculative transaction was started because of the X semantics of the combination. And then we can see some observations tau, like those store and load observations. Next, what could happen is that in this combined semantics, a second speculative transaction could be started, nested inside the outer one. And here, this time, we have a speculation of the Y semantics. And then we can see some actions tau prime that are happening inside this nested speculative transaction. And then we mark with this RLB observation, which is a rollback, that the speculative transaction is terminated. And then we can see the rest of the trace, just some further observations. And then we have this rollback observation for the outermost speculative transaction for this X part. Now, of course, we can swap the order of the speculative transactions. So we can have this start Y outside of it and then nest inside it, nested with this X semantics. So these are the general shapes of the speculative traces for those combined attackers. And now we need to ensure that these actions on these traces are safe or secure. And first, we can divide this problem into 3 sub-problems or 3 regions in the trace. The first challenge is the red area, which is the transaction of X. The second challenge is about the speculative transaction of Y. And the third challenge is the nesting of those speculative transactions. And for each of these regions, we now need to ensure that the observations are safe or secure. So let us go through these challenges one by one. Now for the first challenge. First, let us get some definitions out of the way. We say a program P is secure under the speculative semantics X if it does not speculatively leak more information than the non-speculative execution. And we say a compiler is security preserving for semantics X if for all programs that are secure under the non-speculative semantics, they remain secure when compiled even under the speculative semantics X. Stated differently, this property of the compiler ensures that the countermeasure, here this countermeasure against the semantics X, really works. And for the remainder of the talk, when we see a compiler with only the square brackets, we assume it is a compiler countermeasure against the spectral variant X. Okay, now for the second challenge. We want to combine different spectral versions, and we need to ensure that these interacts nicely with the compiler countermeasure. We call this property independence and extension. Note here again that this is a compiler for X, right? And we state something here with this independent for this version Y. And that is a key difference to the security preservation statement that we have seen before. So what does it say? If this program is secure for the extension semantics Y, then the compiled program should still be secure for the extension semantics Y. This means that there are no unsafe interactions between the compiler countermeasure and the extension semantics Y. This means the compiler does not introduce new leaks under the extension semantics. Now for the third challenge. Here, we require a proof that all observations made in those nested speculative transactions are safe. We call this safe nesting. And we will see later how we can actually achieve this. Okay, with this out of the way, we need to actually talk about what we want to lift. What is the security property of the compiler we want to lift to the stronger attackers? For example, we could try to use our security preservation property from before, that I've stated here again. However, this is actually too strict for our use case. The compiler countermeasures were developed with a specific speculation mechanism in mind to protect against. It never was a goal to protect against other, possibly at this point of time, unknown spectral variants. Now, when we want to lift the security guarantees to a semantics that accounts for additional speculation mechanisms, the compiled program might still contain some leaks that the compiler was not designed to prevent in the first place, i.e., for example, leaks caused only by the additional mechanism Y we combine with, which is our compiler is not supposed to protect against. So the problem here is that our security property cannot differentiate between the two components of the combined attacker. We lose the information from where the attack is coming from. That is why we propose a new criterion called conditionally security preserving. First, note that we now have the two components of the combined semantics in the statement that we want to combine. This allows us to differentiate from where the leak is coming from, solving our problem. Next, we have this additional premise that we assume that this program is secure for the extension semantics. So then we can conclude that this compiled program will be secure under the combined semantics. So in general, conditional security preservation is a variant of security preservation that restricts the preservation only to those programs that do not contain leaks caused only by the additional mechanism. Okay, now we can state our main lifting theorem using these three building blocks. If our compiler is security preserving for X, so the compiler countermeasure really works, it is independent for the extension semantics Y, so it does not produce new leaks for that semantics, and fulfills the safe nesting condition, then we can say that this compiler is conditionally security preserving for those two semantics. Okay, now let us look at how we can apply our lifting theorem on compilers. So here's an example for this fence compiler targeting straight line speculation. In the beginning, we show that this compiler is security preserving for the single variant. This means that the compiler countermeasure actually works. Next, by proving independence and safe nesting, we are able to lift the security guarantees higher up in the lattice. We show that the compiler is conditionally security preserving for these next variants. And we can repeat this process again and again until we actually reach the top for this specific compiler. So what did we show? We show that this fence compiler is conditionally security preserving for this combined attackers at the top of our lattice. And we are able to lift the initial security guarantees to the top. Now on to our main results. We did something similar for 6 other compilers here at the top. And we are able to show one of the top elements in our lattice, again by proving independence and safe nesting. And of course, the security of the compiler itself. Now, we also looked at 2 variants of speculative load hardening. And we can show that these can actually not be lifted to one of the top elements in our lattice. This is because these compilers are actually insecure if speculation on indirect jumps is allowed. They cannot be combined with a J in this graphics. This is what our framework allows for as well. We are able to prove that the inclusion of indirect jump speculation makes SLH insecure. So, as I said, to apply our lifting theorem, we need to prove independence and safe nesting for each of the combinations we want to lift to. However, this results in a lot of proofs you actually need to do to lift those guarantees to some element in the top of our lattice. So to reduce the proof burden, we try to be a little bit smarter. We realized that we can do better for many compilers that we investigated by exploiting the structure of the countermeasure. Namely, with respect to independence, we devised a new property called syntactic independence. Again, independence ensured that there are no bad interactions of the countermeasure with respect to the extension semantics. But for example, looking at a fence compiler, these compilers only add fence instructions into the program, which only stop speculation and do not interact in any other way with the program. So these fences really cannot interact badly with other spectral variants or attackers. So in such cases, we say we have syntactic independence, which we achieve by just looking at the instructions that are inserted by the compiler and the instructions related to the speculative mechanism. And of course, syntactic independence implies independence. Next, for safe nesting, we try to find something similar, akin to syntactic independence. We realized that most of the compilers either stop speculation, like fences do, or capture speculation in a loop, like the red polyne countermeasures do. This means that in those cases, there are actually no real actions on the speculative trace. In those cases, we have a new condition called trapped speculation. And similarly, trapped speculation implies safe nesting. And thread speculation is actually a property of the compiler that we can show for our fence compilers and our red polyline compilers. And with these two new conditions, we are able to greatly reduce the amount of proofs we need to do to lift compilers to stronger attackers. For example, because we proved thread speculation for these 6 compilers, for each of the combinations we want to lift these compilers to stronger attackers, we get the safe nesting property for free. We don't need to prove it for those compilers. So that's the end of my talk. So thank you for your attention. If you have any questions, feel free.
Okay. So I might have not fully understood what you're doing, but I have the impression that for each individual compiler, you lift it up to resist against more attacker. But does that imply properties about chaining those different compilers to be protected against all the attack? Okay.
That would be the next step. As you said, like there's not where here we show really that for one compiler we can lift it to a stronger attacker, right? But it's not that we have like compiler composition.
Okay.
And that's why we have in our conditional security preservation this statement that this program needs to be secure for this extension semantics.
Yeah.
But of course, the next step would be, right, how can you get the security for the extension semantics? Where you first compile it with a compiler for that semantics, right? By showing that this compiler is also security preserving for that extension semantics. However, composing the compilers is actually non-trivial for those security properties. And that's what we're actively working on with a colleague of mine.
Okay, thank you.
Okay, sorry. Do you expect that there are cases where the lifting works, as you have shown here, but the composition does not?
Yes. So one thing we can say is with this independence property that we have, this is actually a necessary condition for composition. So if you don't have, if you take 2 compilers, you don't have like this independence property for each, at least one of the extensions you want to combine with, then you cannot have compiler composition. For example, if you have a compiler that, or I can give you an example, there's a compiler that inserts return instructions into the program. However, there's this other version that like speculates on those return instructions. So where you need to add fences after return instructions, essentially. So now you have like this order problem, right? Where you, if you first do the compiler countermeasure, which introduces new return instructions to protect against a specific spectral version, and then do the compiler which inserts the fences after return instructions, everything is okay. But if you do it the other way around, of course, it's not right, because you miss return instructions that are inserted by the second compiler countermeasure. And there's an actual example for this kind of case. And in this case, you wouldn't be able to prove independence.
Let's thank the speaker again. So the next talk is on preservation of speculative constant time by compilation.
So today I will be presenting this work. My name is Santiago. This is work together with Gilles Barthes and Universidad Nacional de Bahamas en La Porte. You can hear? Oh, okay. So I just look at you. This is work with my co-authors, and in this work we study speculation in the context of security. We show that a proof of concept compiler that we mechanize in Coq preserves. Okay. Moving the flap. 1, 2, 1, 2. Okay. Okay, that sounds better. We study speculation in the context of security, and we show that a proof of concept compiler preserves non-interference even under speculative semantics. Okay. I'll try louder then. So I will begin with the 3 main takeaways of this talk, which are that we model speculation with directives in a verification-friendly way. We want to model predictions from the CPU with respect to branches. So if the CPU predicts that a branch will be taken and is actually taken, we represent this with a step directive. And when the prediction goes wrong for a particular branch, or an adversary mistrains the predictor to get the wrong branch, we represent that with a force directive. Then execution is indexed by a list of such directives that guide execution. Second main takeaway, the interaction between speculation and different compiler transformations. We use transformers for directives and observations to establish the usual simulation diagram to prove preservation. And lastly, we show that a proof of concept compiler with 9 simplified but representative passes preserves the security properties. I will recap the basic example of Spectre v1 that we saw in the previous talk. Maybe I can use this. Okay, I'll try this. Testing. Okay, that's better. So I will quickly recap the example for Spectre v1. Remember, this is conditional branch speculation that we saw in the previous talk. I'll be quick because of that. So I have 2 arrays that are on my stack, A and B. They contain secret and public data respectively. And my program compares an index I with the size of B, performs a load at this position, and then branches on the loaded value. This, as we saw in the previous talk, is dangerous because even though B contains public data and then branching on Y is okay, this, which means that this program is what cryptographers call constant time, that the time that it takes to execute this program is independent from secrets. Under a speculative semantics, this program is no longer secure. The processor might speculate on this branch and execute the access even when the index is out of bounds. When the index is out of bounds, the address can point somewhere else outside B, for instance A, where my secrets are. And Spectre attacks exploit the fact that when the processor rolls back speculation, it doesn't roll back the microarchitectural states such as the cache. So then we can do cache attacks on misspeculated executions. Therefore, we say that this program is not speculative constant time. It's not constant time under speculation. Our goal for this work is to take programs that are secure against Spectre for different kinds of mitigations and to show that our compiler preserves this property, preserves safety against Spectre. This is not so trivial. It's easy to find examples where mainstream C compilers either remove mitigations that we inserted against Spectre or introduce new vulnerabilities to our programs. But perhaps more interestingly is that our compiler that is security-oriented, which is called Jasmine, we informally conjecture that it preserved the mitigations, that it didn't introduce vulnerabilities, but when we were proving our proof of concept compiler, we realized that one of the passes introduces a vulnerability when sharing memory between different arrays if they are secret and public. Luckily, after the fix, all our Jasmine development was still secure. Okay, so to reason about preservation, we need to have a semantics. It's very similar to the previous talk. I will give a quick recap. So we have a semantic like this, where S, which is a state, steps to a state S prime and produces an observation O. The observation is what the attacker can measure about your execution. We have three kinds of observations in our work. For memory accesses, such as loads and stores, we have addresses. So here I'm accessing array A at position E, and I'm leaking the address A with the base pointer and the evaluation of E, that is the index inside the array. Then for conditionals and loops, we have that we leak the evaluation of the condition, E in this case. For other instructions that do not vary their time through their data, we have a dummy observation bullet. In this framework, being constant time is that O, which is above the arrow, is independent from secrets. Now to take Spectre into consideration, this is where we differ a little bit from the previous work. We introduce directives to this statement. So D, below the arrow, it guides the execution. It represents the prediction from the CPU. For instructions that do not need any prediction, such as loads or stores, we have a step directive, which is the usual step that you perform sequentially. Note that we leak the same as before. Now for conditionals, this is interesting. For loops, it's the same because they're both branches. We have a force B directive. B is a Boolean that determines the branch that gets executed. We leak the same as before, the evaluation of the condition, but the branch that gets executed depends solely on this directive that is adversarially chosen. The last directive that we have is for out-of-bounds accesses, which are very common in misspeculated execution. This depends on an out-of-bounds access can access different parts of memory at different points in time, depending on how the compiler lays out your stack. And therefore, we allow the adversary to pick B and I, an array and an index, to access an arbitrary address of their choice. Then with these definitions, speculative constant time, this definition is a little different from the previous talk. We say that a program is speculative constant time if for any prediction behavior D, the observable effect, that is O, is independent from secrets. Okay, now moving forward to preservation, we rely on previous work on preserving constant time, where we establish the usual simulation diagram. We want that if our source is constant time, leaks no secrets, our compilation is constant time, leaks no secrets. And we have the standard diagram where a target state T steps to T prime. We want that S in relation steps to S prime and is still in relation. The key to preserving constant time is to relate the observations, OS and OT. We relate them with a function, a transformer for the observation, that explains target observations in terms of source observations. The intuition being that if OS, the source observation, contains no secrets, then a function of it, which is the target observation, contains no secrets either. To introduce speculation into the picture, we need to account for the directive that the target follows. So the target performs a step under a certain prediction, and we need to find out what prediction the source needs to perform the step that we want. For this, we introduce another transformer, a directive transformer, that guides the source speculation in terms of the target behavior. This is the essence of our approach. So directive and observation transformers to establish the simulation diagram. The general statement for our theorems is as follows. We have a source and target programs S and T. We have a pair of inputs, I1 and I2, that coincide in their public part. They are indistinguishable. And we have a target execution starting from I1 under some predictions D. We want to find a source execution guided by G, the directed transformer, that explains via F, the observation transformer, the observations that we saw at the target, the generality with respect to the previous slide, comes from the transformers taking the whole trace of execution, so all the directives up until now, and the other input. So the transformers can look into the public part of the input, not the secret part. An interesting point is that this approach of establishing transformers for the simulation is complete in the sense that if the pass preserves speculative constant time, then functions exist. The precise statement is as follows. Let's say that we have our source that is speculative constant time, and then these three statements are equivalent. Our compilation is constant time, there is a simulation with transformers, as I discussed, or there is a simulation cube. The simulation cube is the natural extension of how previous work used to deal with constant time. We illustrate our approach with the proof of concept compiler that we mechanize and prove in Coq. Our compiler has 9 passes, such as constant folding, dead branch elimination, array reuse, and RTL generation. In this talk, I will discuss 2 of them. Constant propagation tracks the value of variables and replaces their uses by their values. So in here, we have x that receives 3, and then it can replace the use of x inside the load by the value 3. If we are careful with our analysis, this pass preserves constant time, speculative constant time, because the intuition being that the access to A at position x plus 4 leaks the same as the access to A at position 3 plus 4, which is A7. We need to be careful with the analysis because when we track the value of x, we cannot assume the branches go the way we expect them to. We need to over-approximate branches in a sound way with respect to speculation. To establish the simulation diagram, for this case, is very easy. We pick the transformers, F and G, to be the identity. This means that the programs are in lockstep, and every target step can be replayed exactly by the source. Expressions evaluate to the same values, and thus observations match exactly. Now, a little bit more interesting is dead assignment elimination. So in this program, we have x that receives 3, then the result receives x plus 4, and then we overwrite the result with receiving 2. Then this pass will remove the first 2 assignments because they don't contribute to the final result. And again, if we are careful with our liveness analysis, this pass preserves speculative constant time, the intuition being that dead variables don't contribute to the leakage, otherwise they wouldn't be dead. The simulation diagram is a little more interesting because the source needs several steps to catch up with the target. So we have a target step, and now the directive for the transformer for directives needs to take the target directive, which is the useful step, and introduce a prefix of step directives that execute the dead assignment. In our case, it's just 2. Then the observation transformer takes the source observations. It needs to recognize and remove the prefix of dummy observations from the dead assignments and return the final observation, which is the useful one. So now I will summarize by revisiting the takeaways. We use directives to manage non-determinism and to consider one trace at a time. We can define transformers very conveniently using directives, which help us when proving hyperproperties. We can establish a simulation square instead of a simulation cube, which makes things easier. And transformers characterize a compiler transformation in terms of its effect on speculation and on leakage. And finally, we show that several compiler passes can preserve speculative constant time. We mechanize this in Coq, which you can check out together with the paper at this link. Thank you very much.
Any questions, please?
This? Okay, it sounds working. Thank you. So thanks for the great talk. So my question is that you basically focus on the cache or timing side channel, right? So just wondering, like, could you elaborate a little bit more about how register allocation would impact this speculative information leak or not?
Can I do? Okay. It's so register allocation has we consider a kind of register allocation in our work. We split the pass in two concerns. First, you decide what you want to spill such that you have enough registers, and then you decide which variable goes in which register. The second case is what we consider in our work, and this is checking alpha conversion between two programs. The programs are the same, so this is perfectly fine. The first part is difficult and does not preserve speculative constant time because it introduces new chances for vulnerabilities. And you will hear all about that in the next talk, which Soren will show us how to fix register allocation such that it preserves speculative constant time.
Anybody else? Let me ask a question too. So if you, over here, so you showed the case where you do, you remove this axis to X in the middle. What if that axis that you remove has a memory axis inside, or not?
Yes, that's a good question. So here I was assuming that X was in a register, but we allow, in our framework, we allow removing such accesses if they're really dead. Then this produces fewer chances for mispeculation, and this is fine. In general, again, this is in a context where you have to analyze the program and decide which ones really don't contribute. But yes, this is allowed.
So the final talk for today, SNP, speculative execution and non-interference preservation for compiler transformations, with a subtitle that I let Søren read.
Does the mic work? Yes, all right. So yeah, it's the same idea of the previous talk. We want to secure compilers, but we will introduce this step by step. So let's talk about SNP. And we start with the S, which is speculative execution. And the thing that we want to protect from is spectra. And spectra has this nature, as we have already seen a bit in some talks, that in typical semantics, we do not see it, because typical semantics models program counters, registers, memory variables, but spectra works on microarchitecture, on caches, branch predictors, and all that kind of stuff. So this is an example we have seen already. It's a bounce check followed by a load, and then we use the loaded value as an address. So how does the program step through this with speculation? If we're in this state, we should have an out-of-bounds access, and our if should go wrong, but speculatively, we might execute this statement nonetheless, and therefore load our secret A if we align badly to our register A. And then in the next line, we use our register A with a secret in it as an address. Eventually, our processor, however, will catch up and roll back to the initial state, so A has no longer the value of the secret. However, we have side channel leakage, and this is where we model the leakage in our semantics, that if we have a conditional, we leak the value that we evaluate the conditional to, and if we have an address, we will leak the value that your address has, because we created a cache entry at that address, and that's visible to the attacker. So in the last line, when we use our secret as an address, we will see this in our semantics. Now, branch prediction introduces non-determinism, so we have a different second side to our microarchitecture, and this is the part where our attacker can set up the microarchitecture to guide our semantics. So we have a directive that tells us just as in the previous talk, when we have a conditional, it tells us either to mispredict or to predict correctly. In our example, we mispredicted, so we have a miss here. When we have a memory access, we also give this power to the attacker because we are memory unsafe. We assume the attacker to know the memory layout and the programmer to not exactly know the memory layout. So we give, in this case, the attacker the chance to steer this out-of-bounds access to align with our secret. And then, as we have seen before, if there's nothing to steer about our instruction, we just have a step as a directive. And that removes the non-determinism that comes with speculative execution. Okay, so in general, what we have is an architectural state. We receive a directive from our microarchitecture, we execute our transition, and we observe some leakage to the microarchitecture. And therefore, rather than having to model all the microarchitecture in our state, we can just move our, this should look different, we can just move our microarchitecture only to the semantics, so only to directive and leakage. Okay, so that was the S part. We have semantics, and we can model, we can observe spectre attacks in our new semantics. So SNI is a property that proves absence of spectre attacks. This is what we have seen in the last talk, so I'm going to be quick. We have a state, an initial state, and we divide it into a public and a secret part. And when we have a second state that is equal on the public part, we say it's indistinguishable to the attacker. SNI is a non-interference property that says, okay, give me any two indistinguishable states and any sequence our attacker might steer or program through the microarchitecture, so any sequence of directives. When we execute either of those two states on the sequence of directives, we should get the same leakages because then our attacker cannot observe anything about our secrets because it's the same sequence of leakages. And then for compilers, what we would like to have, if we have source-level semantics that can model spectral attacks, and we have ensured, here's our source program, it has no spectral attacks, it is SNI, and we run our compiler on it, we would like to have our target program also to have no spectral attacks, so to be SNI. And then we say our compiler is SNP if it does so for all programs that we can use in our source as a source program. Okay, let's look at an example. And this is our example is register allocation with a source program being this program. So we have a bounds check followed by a store of a secret into an array, and then we access our array at int. It is SNI because the underlined positions are the only leakages, and they are dependent on public variables, which are not overwritten in our program at any time. Now, register allocation will move some of our registers to the stack because there might not be enough space in our target register set to keep all of them as registers. For example, in our program, we could move int to the stack initially and restore it right before our usage. And the question is our target program now SNI or not? And the answer is not. There's a spectre tag in there, and it follows from the following sequence of directions. So let's go through it with a state. We have our secret here is 42, and the first instruction will just put int to our stack, which will become 0. The second instruction is a misprediction, and since 20 is greater than 8, we will execute this instruction speculatively, and there we store our secret to wherever our attacker likes, basically. And our attacker chooses to align our out-of-bounds test just where our int is stored on stack. So when we restore int from the stack, we will restore 42, and we have a new information flow that was not possible in the source program, which leads to our secret being leaked in the target program. All right, this means that register allocation is not SNP, which partly answers the question from the previous talk, and we did reproduce this with LLVM, actually, and all of LLVM's allocators on code, which is from libsodium's cryptographic library. Okay, with that, our motivation is done, and we can look at two goals. The first goal being, how can we prove if we have a of which we are sure that it is SNP, how can we prove it? And the second question is, can we fix register allocation, which we have just seen to be broken, so that it becomes SNP again? And for this talk, I'm going to focus on the first question. We will do so by example, which is that code elimination. And the reason being that it is SNP. So before we go right into SNP as a preservation, we want to do safety preservation first and look at how people prove safety preservations for programs. Here's our example program. It's a bounce check followed by a load, and then we discard the loaded values because we overwrite it by 0. So a dead code eliminator would probably detect this and replace the instruction, for example, by a no-op. Now, in order to prove safety preservation, what we usually do is we use a simulation relation that relates target and source states. So in dead code elimination, this relation would just state that we have equal states except for the locations that are dead because they do not matter. So as an example, here we have two states. They're equal on all live variables. Just A, which is dead, has different values, so they're in relation. Simulation relation have a second property, and that is the replay property, so that if we have an execution in our target state, we have to be able to replay this execution in a source with the property that afterwards we should end in simulated states once more. And this is a case because even though A is now live at the end of the program, we have equal values between source and target program. All right, so this I call the simulation square, and it induces something I call simulation intervals, which means just stepping a few steps in the target program and some in the source program so that we are in simulation once more. And the nice thing about the simulation square is that we now can do our proof inductively along the source code or along source and target code by just applying our simulation squares once more, and so a whole trace and target program can be replayed in the source program. And indeed, we get a theorem, which is not by me, but it's older, that states if we have a simulation between any source and target program so that the simulation square holds, we get for any safety property that it is preserved by. Usually this is a parametric in P, so that we don't have to create a simulation relation for every source program once more. And another nice property is that we can do our proof without knowing the safety property front up. And we don't even need to know whether this program satisfies it or not. All right, with that, let's look at the advanced version where we move to our speculative semantics. And the naive way would be to say we have our simulation square, we have a semantics, which is new, let's just plug them on, right? Here we have it. If we have a target execution with directives D and linkages L, we need to reproduce that on the source program. Let's look at our example. Let's look at two states that are in simulation, and let's execute something on the target program. Namely, we do the correct branching. I is this time 4, which is less than 8, so we have an inbounds. And then for the knob, we will get the directive step because microarchitecture will not influence a knob. Now in the source program, what we will see is first instruction is easy. We can just replay it, right? Second instruction looks like this. We have a step through our load, which will produce some leakage. And that means we have different leakage between source and target program. Here's another pair of states. We already mispredicted. I is this time 20. And then in a target program, a knob stays in knob, right? Still a step, directive, no leakage. In the source program, we have an out-of-bounds access, and that means our attacker will give us a directive. So we have also a mismatch in directives. So rather than the diagram as we had it, when we receive directives and leakages in our target program, when we're playing, we will actually see different directives and leakages. And with that, we can move to SNI preservation, so SNP, which told us, okay, source program has SNP, then target program should be SNP. Let's look at our example once more, and let's ask ourselves, is our target program SNP? In order to do so, we will have to look at any pair of indistinguishable states, as an example, these two, and we will have to execute any sequence of directives. In this example, these directives. And then we observe the leakages of one of the states, and in order to be SNI in the target program, the other state must have the same leakage. In this case, it's the case, but we would like to prove this. And we would like to prove this in a way that is not, okay, observe look at the full target program and check whether it's SNI, but rather we would like to check this in terms of the source program. So what we do instead of just looking at our our target program, what we do is we create a simulated state of the initial state in our source program and a second one for the other state. These are also indistinguishable. And we translate our directives using our simulation square that we already have. Okay, in this case, this would be this sequence of directives, and we observe some leakage in the left state. Now, we don't even have to think about the right state anymore because we know our program is SNI. We know it has to have equal leakage, and this is the case. Okay, a little bit more abstractly, what is our job? Our job is when we have two indistinguishable states in the target program and two indistinguishable states in the source program that are in a simulation relation, and we execute one program execution in the target program. What we have to do is we have to prove that the other initial state has the same execution with the same leakages. And same execution meaning on the same directives. And in order to prove this, what we can rely on is by simulation square, we can obtain a source trace. And by SNI, for the source program, we know that the second indistinguishable state in the source program must have equal leakages as well. So we can rely on the black part in order to prove the purple part. However, we wouldn't want to do this holistically, but just as we had done for the simulation square, which was an inductive principle which we could move down, we want now to do this for our cube. And this means to look at like a slice in our diagram. When we zoom in a bit and move the frame out of the way, it looks like this, right? It's more or less the same shape. However, we have an issue here. And the issue is that when we look inside the target program and inside the source program, we have something, what is this, right? How do these relate? So we have two states inside the source program. In our original diagram, this was an indistinguishability relation. However, this is only defined for initial states, so we have to do something else here. And the something else is same program counters. So when we have two states, we say they are it's the same program counter when they share the same program counter. And the nice property is this is nice for our induction because initially we have our states to be indistinguishable. They're initial, so they are at the same program counter. So with that, we can rely in induction on the upper part. And we have to prove for our induction to go through that this also holds after our cube executed. Now, I'm not going to go into detail for how we prove the same program counterness. It's actually something that follows directly from the semantics because our leakages leak the program counter. So when we have same directives and same leakages, we will actually end up in the same program counter. So that's moving out of the way. And this is a property that we need to get out of our simulation relation, right? It has to satisfy this cube in order to maintain equal leakages. So we get a similar theorem to the previous one in our paper, which states that if we have a simulation relation between source and target program that satisfies both the simulation square and our new designed simulation cube, then we get that our compiler satisfies SNP. And again, we don't need to know anything about the source program in terms of whether it satisfies SNI or not. We just define our simulation relation parametrically in P and prove our simulation square and simulation cube. So let's have a look at the proof effort that we need to do in order to apply our theorem. First, we have to define our simulation relation, which is the first step. Then what we have to do is we have to look at the direct. And a nice way, as we have seen in the previous talk, is we could employ a function in order to translate the target directives to the source directives. And as a last step, what we need is to rely on this equal source leakage to prove equal target leakage. And again, as seen in the previous talk, we could employ a function here that translates source leakage to target leakage. All right, so in our paper, we applied this method to dead code elimination. in order to prove that it is SNP, and then we tried to do it for register allocation. However, already the first step failed, and that's not surprising because we have seen earlier that register allocation as such does not satisfy SNP. All right, so this answers our first question. Yes, we can prove this with a simulation relation that satisfies the cube. And for the second question, I mean, we don't have much time, so I'm just gonna delegate you to my Prisc talk on Monday, which is recorded. So I encourage you to just look up there how we can fix our register allocation so that it does become SNP. And this I will take ahead, it does become SNP. So to wrap up, we've seen semantics that can model spectral attacks without having to pull all microarchitecture in our state. We have seen SNP as an I, as a property that will guarantee that there is no spectral attack in our code. SNP as a property to convey this through the compiler, and we have seen how to do it by use of a simulation relation that satisfies a simulation square and simulation cube.
We have some time for a question or two.
Very nice talk.
Thanks.
Does the new register allocator lose anything in performance?
Yeah, you have to lose something in performance. So the way I can give you a broad idea on how it works. So what we do is we just take the register allocation as is and run it through. And then we have leakages in our target program. And in order to fix it, what we do is we build a synchronized program between source and target program in order to detect where information flows happen in the target program that don't happen in the source program. Then we statically perform an analysis that will tell us which locations can have different values between source and target program. And those we need to protect.
Hi, nice talk. I was wondering if the extra generality you have with respect to the previous talk buys you something in terms of proving, or you always instantiate these relations between directives and observations with just functions?
Yeah, so I think it is similar. I think Santiago said to me once that his method is complete, so I think we should not have more expressive power with my proof method.
I see. Okay.
Yes, and it's also reasonable to define it as a function, and so I didn't come to any occasion. So if it's complete, I think we don't need anything else.
Okay, thanks.
One more question down there.
Thanks. So I wonder, the target traces, do you assume, so you say they have the same program state, the same program pointer?
Program pointer, yes.
Yeah. So you assume that on both target traces you are making the same speculative decisions?
Yes.
How is that, why can you do that?
You mean why can't the attacker choose different directives on the two traces in order to learn something about secrets? Now this is a very good question because I asked myself this as well, and so far I have not found a convincing answer. The thing is, like the property I'm looking at is not one I thought of myself, right? It's an established property, and this property requires that. So it would be interesting whether there is like something going on. However, my argumentation for it at the end was, if you're an attacker and you execute your attack, you will use one secret of directives, and then you probably know at what point to observe the correct leakage, right? So this is how I would design an attack. So this is probably not the answer that is most fulfilling, but it is maybe at least a hint at why this might be not a bad idea.
Okay, thank you.
Let's thank the speaker again, and this concludes the conference.